day of Today is the second day of the hands-on training on DFT, quantum leaf DFT code mastery. So this program is jointly organized by the Association of Indian Physicists and the Zarnardhan Singh Foundation. Yesterday we have two prominent speakers. One is Arun sir. That is Arun Kumar, Assistant Professor, Department of Physics, Government PG College, Bilaspur, Himachal Pradesh. Arun sir talks about Shista in a very deep manner, in a deep way. He also demonstrates how to install the Shista, how to operate it. Beyond the Shista, he also talk about how to manipulate the properties of materials at a very nano scale, that is in two-dimensional way. Design of the structures using the crystal. And similarly, in the evening session, respected Dr. Deepak Upadhyay, postdoctoral fellow, faculty at Mathematics and Natural Sciences, Cardinal Stefan Wysky University, Warsaw, from Poland. He also joined it, and he talks about very well about the quantum espresso. He gives the detailed insights of the theoretical background of how the DFT has started. So yesterday, both the speakers are well knowledgeable person, and I hope all the participants might be gaining their knowledge. So this is about the brief of yesterday's event. So today we have three more, uh, three more speakers. That is Dr. Upendra Kumar, Assistant Professor, Department of Physics, Triple IT Allahabad. Then Mr. Kaushal Agadha, Assistant Professor, Department of Applied Physics, the Maharaja Sayaji Rao, University of Baroda, Gujarat, and Dr. Sasan Nautiyal, Assistant Professor, Department of Science, Mewar Institute of Management, Ghaziabad. So today we will be getting a lot of knowledge from the speakers, and I hope from this hands-on training, the participant will be able to perform somewhat. They will be able to perform the simulate the material properties using the softwares. There is like Quantum Espresso, Sista, Orca, then Bolstrip. So thank you all. I welcome back again all the participants once again. So good morning, and over to Ankit.
Thank you, Deepak sir. Good morning, everyone, and welcome to the second day of this workshop. And I am chairing this session. And in this session, we have total two talks. One is given by Dr. Upendra Kumar, and another talk will start at 12:30. That is from Kaushal sir. So, Dr. Upendra Kumar, he is an assistant professor in Department of Applied Science at Indian Institute of Information Technology, Allahabad. His study was mostly in the field of experimental condensed matter physics and material science. He earned his BSc and MSc in solid state physics from BHU, and further he has done his PhD in physics from IIT BHU. During his PhD, he focused on RP oxide and peroxide oxide materials. His research interest includes experimental and theoretical condensed matter physics, electroceramics, renewable energy sources, and spintronics. He has published more than 70 international and national research papers in various reputed peer-reviewed journals. Further, he has published 5 book chapters and he has 8 ICDD database. Currently, he is running 2 research projects from SERB of 51 lakh and seed grant from Triple IT Allahabad of 10 lakhs. He is also an associate editor in various reputed journals. Currently, 5 students are doing PhD under his supervision. He's presented his research work in various international national seminar, workshop, and conference. Today, he's going to give invited talk on electronics properties of cubic fluoride cerium dioxide using Wing 2K. So, Dr. Upendra
You,
sir can
yeah.
enlighten us with your talk.
Okay, so thank you, Dr. Ankit sir. Am I audible to all of you?
Yes, yes, you are very much audible to us.
Okay, so thank you so much, sir, for the brief introduction of mine. And I think now I can share my slide.
Yes, please.
Yes, yes. I
Sir,
think,
your screen is visible to us.
okay. So,
Yes.
should I start?
Yes, yes, please. Sir.
Okay. So, very good morning to all of you, and very good morning to the all associated members of AIP, that is the Association of Indian Physicists. And thank you so much for giving me this opportunity to share my research work or experiences with the young minds. So now I'm starting. So today since Dr. Ankit sir has already told about that I have worked on the theoretical as well as experimental condensed matter physics. So today I'm just give brief introduction about the DFT from atoms to solid, and one research article that I published that is on based on the cesium germanium bromide. Uh, now, so my presentation includes the following outlines, that the theoretical background of the DFT, why we need DFT, then many body theory, then how we apply various approximation methods to normalize the exchange potential, correlation potential, and the different types of potential functions, then density function theory. And the part two contains the hands-on session. So here I'm just showing you the relaxation of a crystal structure, that is cesium germanium bromide and cerium oxide. So the cerium oxide part has been done, will be done by my student, Rajkumar. He will join the session after mine. So now I'm starting. So why density functional theory, why density functional theory is very popular. So since here most of the students are PhD and PG students. So since in quantum mechanics, the lesson is uh, first lesson is associated with the Schrodinger wave equation. So when we solve or when we do the quantum mechanics, then we need some wave function and some energy expressions. So means we want to study the mechanics of any quantum particles, which is not visible to us by the naked eyes. Then we apply some wave theory that is associated with the Schrodinger wave. So in further, if we move from the Schrodinger wave to the real problems, that is hydrogen atom. So everybody knows that hydrogen atom is a one electron and one proton problems. So here the proton, there is a one proton and the one electron. So there is a very much easier to solve the Schrodinger wave. So here I'm just giving you a brief explanation about the wave equation. So this one, yes. So this one is the Hamiltonian for this hydrogen atom. If there is a one single hydrogen atom, then there is only one single potential and the one single kinetic energy terms. So when we write the Schrodinger wave, that is the H psi is equal to E psi, where H is the Hamiltonian of the system, that is given by the addition of kinetic energy as well as the potential energy. Means when you add the kinetic energy of the electron and the potential energy of the system, why we call it as a system? Because there is a one electron and the one proton. So when we study the potential, there is a one correlation between the electron and proton. So that's why in that case, the potential is instead of E by R, that E square by R. So here you see, because here I'm writing for the more than one electron system. So here you see E square by R. So that is for the association between the electron and the proton. That's why here the potential is instead of E by R, that is the E square by R. So, and the kinetic energy is, everybody know that the P square by twice R. So in quantum mechanics term, we write P as the momentum operator. So momentum operator is given by H bar by I, del by del x. So that's why here we have used the del operator. So when we solve this one electron problem, then we find this the psi 1s means the wave function for the 1s orbit is 1 by root 4 pi aq e power minus r by a. R is the radial distance, a is the Bohr radius, and in this manner we find the energy as minus 13.6 by n. N is the excited states or the higher energy states. If you want to find the ground state, that is n equal to 1, first excited, n equal to 2, n equal to 3 in this manner. But what will happen when we consider the more than one electron system, like helium? So in the case of helium, that is a 2He4. So here the number of proton is 2 as well as the number of electron is 2. So how to find this Hamiltonian for the two electron system? So here the some complexation is come into picture when you write here we write for the single electron and for the another electron the potential for the that one, that is the single electron in the individual electron, and this terms comes into picture that is due to the interaction between these two electrons with each other. So the total Hamiltonian for this system is minus h bar square by twice m del 1 square minus h bar square twice m del 2 square plus jd square by r, 1 for the first electron and r2 for the second electron, and r1 minus r2 is the mean distance between these two electrons. And when we solve this, the wave function comes to be 1 by under root 2 times phi 1 r1, phi 2 r2, chi 1 2. Chi 1 2 is representing the spin's energy states. Like if one spin is up, one spin is down, so chi 1 2 comes into picture as one is the positive spin, for the another one the negative spin. So this n electron problem was solved when Cohen and Sam in 1965 formulated a theory concerning three-dimensional electron density and energy function. So this is just a brief introduction why we need DFT, because if there is a number of electron you increase, there is a complexation comes into picture, then we are unable to solve the Schrodinger wave equation. And when we can't solve the Schrodinger wave equation, then we can't find the energy states and the associated energy wave function. So why we need the DFT? Because for the more than one electron system, we need some another theory which solve these problems. So the electron density that is given by n of function of r, r is the radial distance, plays central role instead of wave function. Means in case of the density function theory, instead of considering the wave function, we consider electron density. The problem of many interacting particle system in static potential is reduced to non-interacting single particle system in an effective potential. In this manner, we solve easily the more than one electron problems. So what will happen? Yes. What will happen when we consider many body problem? So for large interacting system, we first need to consider a many particle wave function. And then many body Hamiltonian comes into picture for electron, and the nucleus is of the form as given below. So this, as I already told you, that Schrodinger in 1926 gives his theory based on the wave particle nature. Because if a PG students is available here, then he knows very well, or they can know very well, that there is some issues in the classical physics that can be solved by the quantum mechanical assumption that is given by the Schrodinger wave theory. So how we see the Schrodinger wave, that is H psi is equal to E psi. So here we represent capital M for the nuclear, small m for the electronic, and E for the mixed. When there is a mixing is when both electron or both electron in the nucleus, then we use small e. So here the kinetic energy term for the this is for the nucleus, this is for the electron. So h bar square by twice del 2 square H square twice ME, that is for the electron. And these are the potentials that I already told you that when you consider the more than one electron problem, then you have to choose the potential very carefully. So here for the one electron, there is a Zn into Zm E square by Rn minus Rm. And for the only electron interaction, then E square by Rm minus Rj. And when there is an electron is interacting with the nucleus, that is Ri minus Rn. So these are the different potential terms when we consider more than one electron system in the theory. So here the total Hamiltonian is given by T of capital R is V of capital R, that is Hamiltonian for the nuclear. This is for the T of small r, and V of small r, that is for the electron. So means we are just adding the nuclear part as well as electronic part. So this is the total Hamiltonian in this case. And this is for the only, because if you consider the mixing, there's only change in the potential, not there's a change in the kinetic energy. So only the potential is comes into picture for the interaction among the electron nucleus, nucleus electron. That's why here the another last term is present. So what type of approximation is made? How to hide this? Yes. Approximation for solving many body problems. So there are several theories available in the literature. That is in first one, the Born-Oppenheimer approximation. Second one is the Hartree approximation. Third one is Hartree-Fock method. And fourth one is the Cohen model. And the last one that is very much acceptable for the DFT is the Cohen-Sam approach. That is based on the name of Walter Cohen and Lou J. Sam. So we just first discuss how these approximations solve the issues that when we consider the more than one electron system in the problem. So Born-Oppenheimer approximation is simply solved by when they consider nuclei are much heavier than the electron. If you consider one particle or the one body is a very much heavier and relative to which the electron is lighter, then we consider the nuclei has the zero kinetic energy, because when the body is heavier, they can't move. So as we just assume this approximation, then the kinetic energy terms for the nuclear is vanishes, and only the potential energy terms remains to be present here. So now, and the second approximation that they have made is they move much more slowly and hence neglect the nuclear kinetic energy. And the third assumption in their theory is the wave function separated into electronic and nuclear part and determine the motion of electrons with nuclei held fixed. Just like in case of our solar system, where sun is fixed and all the planets are revolving around them, the same theory is applied to here. When we consider nucleus is heavier, they can't move, then they have the zero kinetic energy. And as they have zero kinetic energy, then you just assume that the nucleus is in rest position and associated kinetic energy is zero. And the may rest part, that is the potential energy, is present here, and only we consider the electronic part in the system. So in this case, as we apply this approximation, then the total Hamiltonian for the electron and the nucleus is T of small r plus T of capital R, V of small r, V of small r into R, and V of capital R. So when we just assume this Born-Oppenheimer approximation, then the kinetic energy term vanishes and this race term is available. Then the Hamiltonian for the electronic part will be this, and the nuclear part will be only
हाँ
this.
तो नहीं मैम सारे सोफे हटा हटा के झाड़ू लगा दो
What?
आपकी चीज दो तो वहां रख देती है, हमको दे देती है, टेबल पर रख देती तो वहीं की वहीं मिल जाती चीज।
ये कहाँ रखी
Is there an issue?
No, sir, continue.
Okay. So when we consider this electronic Hamiltonian, then this can be given by this minus 1 by 2 times del square I plus 1 by 2 times then 1 by 2 times E square by Ri minus Rj minus Zn times Ri minus R capital N. So now the second approximation that is given by the Hartree approximation, that is also known as one electron model. So how they just apply this approximation? They just reduce the complexity of electron-electron interaction. Okay, means if there is a more than one atom is available in the system, then there is also interaction among the electron-electron taking place, and due to we just reduce the complexity, so then we just treat those electron-electron interaction in terms of independent electrons. So how the electrons are independent and interact with others in an averaged way. Means we don't focus on directly to the electron-electron interaction. We just focus electron is interacting with the rest field. If you just consider the one electron. So for an n-electron system, each electron does not recognize other as single entity, but as a mean field. Means if there is 100 electron is available and we focus on the first electron, then means there is 100 interactions available, because for 1 to 2, 1 to 3, 1 to 4, in this manner 1 to 100. But here, instead of considering individual interaction, we just consider the interaction between the one electron with the mean field of the rest electrons. So we have just reduced the complexity and we just ignore the electron-electron interaction. So for an n-electron system, each electron does not recognize other as single entities, but as a mean field. So this is the main approximation, the main part of this approximation theory. So hence, an electron system becomes a set of non-interacting one electron system, where each electron moves in the average density of rest electrons. So just like here, we just showing with a picture interacting particles and there's the independent particles. So here the self-consistent field procedures to solve the wave equation is this, because here just we reduce the mean magnetic field. So this is the V external is the, here we have already written, R is associated for the nuclear, small r is associated for the electron, V external is the electron and nuclear interaction potential, and VH, that is a Hartree potential, because this approximation is known as Hartree approximation. So here the Hartree potential is denoted as electron-electron interaction. So VH is the potential of the interaction between the electron with the rest of entities. That is the mean field of the rest of entities. So in this manner, we can solve the whatever the issues we have just seen during the many-body problems. Now, as Hartree method produced crude estimation of energy due to two oversimplifications, Hartree method, so there is some also drawbacks. So Hartree method does not follow two basic principles of quantum mechanics, that is the antisymmetric principle and the Pauli exclusion principle. How? Antisymmetric means when you apply some the antisymmetricity to the wave function psi of x, it gives you minus psi of x. And Pauli exclusion principle is that means two electrons can't be placed at one single state in their same spin value. Means two spins can never be sit in a single place if those have the same spin. And it also does not count the exchange and the correlation energies coming from an electron nature, because we have just assumed there is a n non-interacting particles with one single electron. So that's why there is some drawbacks. So this drawback is further solved by Hartree and another scientist, Fogg. So what they have done by the Fogg is that based on the one electron the mean field approach by Hartree, V.A. Fogg enhanced the methods to high perfection. How? They have generalized the Hartree's theories to take into account the antisymmetric requirement, because there is a two major drawback of the Hartree that antisymmetric principle and the Pauli exclusion principle is not followed in their theory approximation. So in this case, they have in Hartree-Fock method, The n electron wave function approximated as a linear combination of non-interacting one electron wave function in the form of Slater determinant. So the Slater determinant defined as psi of 1 to n, and these are the wave functions. So in this manner, we just find the Slater determinant. Now, when we consider this wave function, then this value of total energy is changed, and this is for the E kinetic energy. EH is the Hartree interaction, and E external for the nuclear to electron interaction. EX, that is another term which comes into picture by the considering the antisymmetricity of the wave function. Then the EX is the extra energy comes from the antisymmetric nature of wave function in the Slater determinant. Now, what is the difficulty with Hartree-Fock theory? Again, the first one is the correlation energy and the problem of dealing 3n dimensional. So, how to solve these problems? That is solved by the new approach, that is density functional theory. So, in this density functional theory, the main objective of DFT is to replace the many particle electron wave function with the electron density as the basic quantity. So here I just want to clear, when we study the quantum mechanics, then we know the wave function is important for us. To solve any problem in the quantum mechanics, we need to find the wave function associated with the electron. But when we consider more than one electron system, then there is a several issues comes into picture. And if we go for solving those issues, then there is it is very difficult for us to solve those issues. So instead of considering the many particle electronic wave function psi 1, psi 2, psi n, we just consider the electron density. Okay, the electron density, the central player in DFT decides everything in an n electron quantum state where there is no individual electron density, but a three-dimensional density of electrons. And the addition of all the electron densities over the whole space naturally return to the total number of electrons in the system. And this theory gives approximate solution to the both exchange and correlation energies. Means all the issues what we have faced during the previous approximation is solved by considering, instead of wave function, we consider the electron as a density, electron density. That's why this theory is known as density functional theory. So what will happen? That is when they have considered density function theory, the first approach is done by the Cohen and Sam in 1995. So Cohen and Sam is replaces. I'm just taking 1 minute. Okay. So sorry for the so the Cohen and Sam replace the interacting n electron system with a system of one electron system in an effective potential having the same ground state. That's why when we talk about the density function theory, it is clearly indicated when you study the ground state properties and when you study the first excited state the properties. So both are the, for both things, the theory is little bit different. So here we are just only considering the ground state property of the system. So as we know, the energy for the system is given by E of kinetic and E of the EXT stands for the nuclear to electron interaction. H is associated for the Hartree term. X is associated for the Hartree-Fock term. And EC is the when we consider the electron density approach. So that's why all these energy is added, and the kinetic energy is simply for the non-interacting systems and the interacting systems. So when we solve this theory, then we find the total energy as the function of nr, that is the density function, and ext is associated with the nuclear to electron interaction because all the electron is in the ground state. So we consider only single electron interaction potential. So Cohen and Sam equation has the form of this h square by twice m, and the V effective is given by the ext, that is for the nucleus to electron interaction. H is associated for the Hartree interaction, Hartree term, and Hc is associated for the Hartree for an electron interaction term. So how we just solve this? So replace the original many-body problem with an auxiliary system for non-interacting particles, that is interacting electrons with the real potential. And hence the final Cohen-Sam equation has the form of Hks is equal to this. And where the VH Hartree terms is given by N of R prime. N is for the electron density at a distance of R prime. Hc for the electron density interaction among the electron, that is given the delta of Exe divided by delta of Nr. So Nr is given by I is equal to 1 to n mod psi r square. So how this theory is normally work for the any system. So these are the several steps when we just doing the DFT, or when we just apply the DFT model to the any system. So first, as we know that instead of considering the wave function, we just consider the electron density. So initially we guess, or the software as available the exchange potential, available the correlation energy functions, they just initially guess the NR value and then calculate the effective potential based on this NR and solve the Cohen-Sam equation and calculate the again electron density. So initially we just give some initial guess of the electron density, and after this solving this Cohen-Sam equation, they find the actual NR value, and if the difference between this NR and this calculated NR is very less, then it is consistent. If it is not less, if one is 100 and another is 1000 or 1 lakh, then this is not self-consistent. Then again, this value change, and this process is continued up to when we find the consistent solution. And the output quantities will just like potential energy, static structure, bond effective charges, and so on. So now we are just focusing toward the exchange correlation approximation. So this is the Hartree world where the different types of potentials are available. So there are different types of exchange correlation approximation. One is LDA, that is the local density approximation. There's another one, the GGA approximation, meta GGA approximation, EXX with correlation, EXX with partial exact correlation. So what are the basic things is that in LDA, we just consider local density. In GGA, we just consider the difference of the local density available around the system. And in the meta GGA, we just consider the del square N of R and the relaxation time. And EXX equation, we just only focus towards the occupied energy states. And the last one is the empty. We are just focusing towards the unoccupied states of the system. So what is the local density approximation? This approximation used to find out exchange correlation function. Exchange correlation function energy is purely local. Local means we just focus towards the local electronic systems available around the system. Like if we focus the one nucleus surrounding 1 electron, 2 electrons, 3 electron, we just only focus towards the not the 1 to 100 electron, 1 to nearest and neighbor electron system. And it ignores the correction to the exchange correlation energy at a point R due to nearby inhomogeneities in the electron densities. Now the second approximation is generalized gradient approximation, that is depends on the local density and its gradient. That's why here I have used the del. The del is for the gradient. And GG also uses information about the local electron density and also the local gradient in the electron density. Though GG includes more physical information than LDA, it is not necessary that it must be more accurate. Means the basic thing is behind this that it is never you can be sure that If we focus towards the each individual interaction, then it gives you the accurate value of exchange potential. Okay, so always we have to apply both LDA as well as GGA, and based on the literature available, we just compare our result. And for those, if we need the more accurate value, or there's a difference between the literature value and our experimental theoretical value, computed value is very less, that is acceptable. Otherwise, we just change for the approximation theory. There are large number of distinct GGA functionals depending on the ways in which information from the gradient of the electron density can be included in a GGA functional. Means if you just change, there is a change 1 to 3, 1 to 4, or 1 to 5 interaction, then there is a change in the GGA function. So that's why here we can't find the one GGA function. There is a number of GGA function is available. As you consider the what type of interaction between the electron, or other rest of electrons. Now density function theory. So as we already we have known about the what is DFT, and based on this DFT theory, there are several models or several software is available in the market, in the scientific community. That is a quantum espresso, ELK, VAST, Castep, AB initial, and the Win2K. And also there are so many software is also available based on the different types of exchange correlation potential and rest of the things. And what type of property we measure from this DFT theory is that electronic band structure, equation of state, elastic constant, atomic charges, Raman infrared spectra, lattice dynamics, and optical properties. So here I'm just showing you a few examples based on the Win2K software that I have run in my lab using Win2K. So what will we do today is that total energy and relaxation for the here I'm just giving you an example because silicon is a more well-studied material in among the various PG students also. If they have done your project on the computational, they can easily solve the silicon problem. So there are several steps in solving the DFT or problems. That is, first we create the file, that is an input file. Then we run for the STM, that is the relaxation structure formula. Then we go for the E-cut, that what are the dimension of calculation you want to be calculate. Then we find the K point. Then we find the VC relax points, rho, that is a charge density, DOS, density of state, electronic bands, and phonon modes. So these are the several things that you can measure from the DFT. So here I'm just giving you one example, that is the cesium germanium bromide. This is the well accepted material as a solar cell material, and that is used as an active layer, that is also used to enhance the photo conversion efficiency of solar cell. So this is the basic parameter. So when you run any program in the DFT in the Win2K model, then you need the lattice space group, their Wyckoff position, their elemental information, atomic coordinates, lattice constant, lattice angle, and volumes. And also you have to know about the ionic radii. Okay. So these are the parameter that for the cesium germanium bromide, it is a cubic crystal structure crystallized under the PM minus 3M space group, and the Wyckoff position is 1A, 1B, and 3C. For the cesium, the position is 0, 0, 0. And for germanium, this is position is half, half, half. And for bromide, it is half, half, 0. Okay. While the lattice, why I am just telling you the lattice constant, because this is the some assumption model that they have applied to this structure, and they find this value of lattice parameter. But when you solve using the different potential models, it is not necessary you get the same value of lattice constant as you supplied during the calculation, because each structure or each potential has their own convergence point for the relaxing the crystal structure. That's why you have to focus on the exchange potential. If you change the exchange potential, you just change the relaxation structure. And if you change the relaxation structure, then you just change the property of the material. That's why these things are very necessary when you go for the solving the DFT model for the any material. So as example here, cesium, germanium, bromide. So how do you relax the structure? So first in the Wintuke software, we just apply the X-Cris day. That is the tool available in the already in the software. We just created the structure based on the these atomic coordinates. These atomic coordinates, you just generate the crystal structure, and then we just apply the SCF calculation. SCF calculation means structure relaxation calculation. And when you just apply, you find the x-axis is the change in volume percent and y-axis is the energy. So the lowest value of energy and the lowest value of energy gives you the most relaxed structure. So here we just see the energy volume optimized curve in figure. This it shows the minimum energy occurs around 1210 Bohr cube. That is the change in the volume. So based on this change in volume, we have just calculated the lattice constant after the relaxation was found to be 5.6477 angstrom, which is higher than the experimental value that I have just applied here. That is a 5.53. So as we apply the Wintuke model to this system, we just get the different value of lattice constant. And this value of lattice constant is higher than the reported. It means there is some change in the structure or change in the defect. Okay, because as we all know that it is very impossible to create a material with 0% defect, because it is not possible. So that's why here we just find this value of lattice constant that is different than the experimental or the supplied one is due to the lattice defect present in the system, which is associated with the exchange potential. Okay. So now the another theory that I have studied using this is that band structure plot of cesium bromide. This B figure indicate the density of state for the cesium bromide. C is indicating the partial density of state, showing major contribution of elements. Okay. So what are the things that we can calculate from the electronic band structure is that here we just find that when you find the value of optical band gap, you just go for the R point. Instead of going to another points, you just go for the R point, which is close to this energy axis. And here you see the difference between these to this. Okay. So as we find there is a difference in the value is 2.325 electron volt. That is the this separation to this separation R point and divided by 2. That's what it gives you the value of 2.325 electron volt. So how the band is formed in any material. So just in case of the perovskites, if the perovskite is ABX3, then the major contribution of the band gap is associated with your metal cation, that is the B atom and the N ion. Okay, so only these two atoms are responsible for the formation of band gap, that is the valence band and the conduction band, so that the mostly the dominating part of the band structure is the germanium and bromide. So here we can see it has been observed in this figure that the majority contribution of germanium and bromide is taking place. So here we see the cesium contribution is not so much because only the contribution of germanium and bromine is taking place. In addition to DOS, we can also calculate the partial density of state, where again we see that the p orbit of germanium and the p orbit of bromide has a major contribution in the formation of the optical band. Okay. Now the partial density of state, we can also calculate the partial density of state. So here we see the this is the partial density of state. The cesium has the d orbit contribution, bromine has a p orbit, and germanium has the p orbit. So here we see this, the contribution of germanium and bromine is taking place in the major cases. While in case of the cesium, again there is a contribution, germanium is dominating. So the major contribution to DOS is attributed to the germanium atom. Here we can see, and it suggests the existence of delocalized electronic state that facilitate effective charge conduction and transport. Also, the electron density plot, as shown in this figure, enable us to comprehend the distribution of electrons in each isocline, which represent a constant electron density value, indicating the regions within a material where electrons are distributed similarly. So these are the different regions of the electron distribution. Okay, because most of the time the students can't get the point what the things they have to explain their research article or they're in the research paper. Now we have just calculated the electronic properties. That is the first one is the real part of dielectric tensor. B is the imaginary part of dielectric tensor. C is the refractive index, and D is the extinction coefficient. So the electronic part or electronic property of the material, that is the dielectric real and imaginary tensor of the dielectric part, is calculated by this Kramer-Kronig relation, where P is the polarization in the material, epsilon 1 omega is the real part of dielectric, and epsilon 2 is the imaginary part of dielectric. Okay, omega is the frequency that can be easily converted into the energy. So one more thing here I want to clear, when you just go for the DFT calculation, that dielectric property is just reverse of the optical property as well as the electronic property. When there is a, if we consider that dielectric constant is arises due to the polarization is existing between the materials. So if there is a polarization, then charge is not mobile, charge is separated. And when charge separated means there is a low value of conductivity. So always you just keep it in mind that these things, that when the dielectric value is higher, the corresponding conductivity of the electronic property is lower. Okay. And when the electronic property is lower, the optical property associated with it is higher. So again, the value of refractive index and the extinction coefficient is calculated by this formula. And here we see the most of the absorption is taking place, or the dielectric is lying in the range of the less than the 4 electron volt, which is generally the semiconducting nature. And here we see when this absorption or this dielectric is higher, imaginary part is also corresponding higher. Okay, and the refractive means all these things are correlated with each other. That's why here I'm showing you at the same time, because you just get the information and you can easily correlate all the things with each other. Okay, so here we see the dielectric part is very much higher in this region, and you find this higher region in all the samples, all the calculations. Okay, now okay, now the next part that I have calculated is the optical properties, among which absorption coefficient, real optical conductivity, imaginary optical conductivity, and the optical reflectivity. So here on the basis of TB MBJ potential. So as I earlier told you, if dielectric is higher, then the corresponding conducting property is lower. So here you see that, because when the electric field, when you apply some small electric field to the system, there is a polarization taking place. And when the polarization is taking place, there is a no movement of charge. If there is a no movement of charge, there is a no absorption, there is a no conduction of the charge carrier. That's why here we see the just reverse of the dielectric function behavior in case of the absorption coefficient, optical conductivity, imaginary optical conductivity. So those things, when we find for the less than 4 electron volt, there is a higher value of dielectric function. real and imaginary. So here corresponding absorption coefficient is lower, as well as the optical conductivity is the comparable to the literature. So here the imaginary optical conductivity as shown in figure 5c is negative up to -6 of electron volt. Okay. And because there is a -3 to +3, that's a -6 of electron volt, +6 of electron volt, suggesting some sort of the stimulated emission. Because when any radiation is absorbed by the material, then there is a certain non-radiative loss as well as the radiative loss is taking place, due to which the stimulated emission taking place in the system. And that's why here in a small absorption coefficient, instead of having a large value of epsilon2, that's why your absorption coefficient is a little bit small, although there is a large value of epsilon2. Optical reflectivity refers to the measure of how much incident light is reflected off material's surface. Okay, means if the reflectivity is higher, means you get the low value of conductivity. Because if all the radiation is incident on the surface, is reflect back, then there's only less amount of radiation is absorbed and conduct during the material, with the material. So now the next that I've calculated is that the number electron density, density of state, electrical conductivity, and thermal conductivity. So these are the formula for calculating the electron density. You can also get this formula from my paper. And when you calculate the number electron density using the density d of epsilon, that is the density of state that I calculated earlier. So when you apply, we find that this number electron density is higher in this when the chemical potential is negative, and lower when the chemical potential is positive. So, and what about the DOS, density of state? Well, how it is changes that below the this chemical potential, below the negative chemical potential, there is a high density of state. It means the most density of state is associated with the electron. Okay, that's why there is a negative value of chemical potential is existing. Now, electrical conductivity is calculated for this. That is find very high value of electrical conductivity below the 0 electron volt chemical potential. And corresponding thermal conductivity is also measured using this transport distribution function. And we find that there is a significant change in the thermal conductivity with the change in the chemical potential. Now the thermoelectric properties has also measured using the WorkShop software, which is available within the Wintuke software tools. So first we have calculated the Lorentz number, which Lorentz number is used to calculate the rest of the thermoelectric property. So Lorentz number is calculated by this formula, that is a C electron. One more thing that I want to clear here, if you are using the WorkShop, they have only considered the electronic specific heat. Means they can only consider the electron available in the system and contributed to the thermal conductivity, not the lattice. So that's why here we can think we need to change some models, but as we already assume that nucleus has heavier, it is in rest. So there's no significant impact of these things on our Seebeck properties, thermoelectric properties. So we have calculated the Seebeck coefficient for this system, and we have found that below the chemical potential, in the negative chemical potential, there is a positive value of Seebeck coefficient. However, if the chemical potential is positive, there is a negative Seebeck coefficient. It means if the chemical potential is positive, the mostly dominating charge carrier negative charge, and when chemical potential is negative, the mostly dominating charge carrier positive charge. So these things you have to clearly mention in your manuscript. Okay, now we have calculated the power factor that is given by S square sigma. S is the Seebeck coefficient and sigma is the electrical conductivity of the material. So here we have just calculated and we found that for the positive electron potential, the power factor is very higher. It means for the negative charge carrier, the power factor is dominating. Okay. Instead of hole contribution, there is a majority of electron contribution is available in the system. Then we have also calculated the specific heat as well as the magnetic susceptibility. Okay. So here the specific heat again shows that for the negative chemical potential, the specific heat is higher. So here you can just understand, if the charge carrier is conducting the heat, then they can't conduct the conductivity of the electrical conductivity instead of thermal conductivity. Means the charge carrier which is contributed towards the thermal conductivity is not participating in the electrical conductivity. So if for the chemical potential where the specific heat means thermal conductivity is higher, there is a corresponding power factor is lower. And when the thermal conductivity is lower, the corresponding power factor as well as the Seebeck coefficient is higher. And these things also is significantly shows in the magnetic susceptibility. Okay. And now the next part is Boltzmann transport equation that can be done after few times. So I think this much is enough, because if at one time if I will give you all the introduction, then it is not good for you to learn. Okay. So if committee allow me, then I can continue the Boltzmann trap model also. Thereafter, some hands-on session will be carried out.
Sir, you please continue with the hands-on. And after that, after lunch break, I request you to
Actually,
talk
after
about.
this, there is one more meeting. Then I will told my student to give you brief detail about the Boltzmann transport equation.
No issue, no issue, no issue, sir, no
Okay.
issues.
I think after 5 minutes, Rajkumar, just join the system. Sir, I will. Huh? So wait for 5 minutes only. I'm just connecting to the server. Okay.
No issues, sir, no issue.
So anyone any query?
Namaskar, sir. Sir, I have one question.
Yes, ma'am.
Sir, in the Seebeck coefficient or chemical potential graph, you
Yes.
change the heat, temperature, like 200 K, 300 and 400. So how you give that?
This Boltzmann trap software editor tool, they have given you the different temperature value. So
But-
in that, this is available in the software. At what
So,
temperature range you want to calculate the Seebeck coefficient or power factor?
okay, sir. So it means that we can give the different temperature
Yes,
according
we
to.
can provide a different temperature. Yes, ma'am.
Actually, sir, I'm working on experimental as well as theoretical part. So in experimental, I change the temperature. So it is possible to change in a theoretical also
Yes, it is
as per
available in the
my
theoretical
required
also.
temperature. So please, sir, can you show in your hand-on-hand training how
Actually,
we can?
this part is done by my student, which is a little bit busy, but I will take the time from him and then I will show you how to just calculate the Seebeck coefficient at different temperature value.
And sir, if the material is not magnetic property, then we have to calculate all these or not necessary for.
Ma'am, it depends on your interest. If the metal has non-magnetic, then as I already told you that some magnetic characteristics is present in the material is due to the defect. So if there is some defect, then you can find some magnetic properties also. So these things also support your the results. And If it is not available, or if your material is not non-magnetic, then simply you just go for the rest of the calculation instead of the magnetic calculation.
Okay, sir. Sir, one more favor from you. I
Yes,
want one more favor from you. Sir,
yes,
how we optimize, आपने अभी समझाया था latest volume optimization.
yes, yes. These things.
Sir,
Yes.
can you please re-explain?
Actually, when you just run the calculation, SCF calculation, then you find the graph between the energy change as well as the volume change. So where this change in volume is very minimum, with the
Yes, sir.
minimum value of energy, this much is acceptable.
ओके सर, मतलब ये वाला जो मिनिमम एनर्जी होती है उस
पार्ट,
पॉइंट पे
यस
हमको
यस यस मैम, यस मैम। क्या होता है कि अगर आपका क्रिस्टल स्ट्रक्चर है, कई पोटेंशियल आप अप्लाई किया उसमें, तो क्या होता है कि ड्यू टू अवेलेबल इलेक्ट्रॉन डेंसिटी, देयर इज सम इंटरैक्शन बिटवीन द इलेक्ट्रॉन न्यूक्लियस, इलेक्ट्रॉन इलेक्ट्रॉन, द स्ट्रक्चर इज नॉट रिलैक्स्ड. So when the structure relaxed means the negative value of energy should be minimum, and
ओके सर.
the minimum value of energy is acceptable.
So sir,
Instead of for this,
how you find the lattice constant from this graph?
yes, in the output file, you just find for the when the if, change in volume 15%, the corresponding calculation is already given in your output file.
Okay sir.
Hello,
But
sir.
sir,
Yes, yes, ma'am.
okay,
Yes.
thank you sir.
Okay, okay.
Hello,
We can
sir.
also discuss. I will share you with my mail. You can also discuss your query on my mail also.
Hello, sir.
Okay, thank you so
Yes.
much sir.
Okay. Okay. Yes, ma'am. Yes, sir.
Hello, sir.
Yes,
Hello.
sir. Yes, yes, yes.
Good morning, sir.
Good morning.
Can you suggest couple of books which gives theoretical aspects of this, whatever you have discussed?
Actually, when we are going for the research investigation, then there's no single book is available, because all the books is just writing there the pre-assumption theory that is from the 1965, that I've already discussed these theories in the which is available in the book.
Yeah.
But when we go for the some research oriented investigation, then we go for the research articles instead of going for the book. But for the basic things, you just go for the book that is for the I will give you the name. One second. Because here I'm already
Excuse
running a
me, sir.
course. Yes, ma'am.
Sir, please
Yes,
post this chat box. Thank you, sir.
Okay, I will type in the chat box.
Yeah,
the
yeah.
book
Thank you,
name.
sir.
Okay, okay.
Sir, can you please share this PPT after the session?
I will share the PPT, ma'am.
Okay, thank you sir.
Okay.
Sir, there is one more question in the chat. Can this
Around
can
my
apply this for
electron
magnetic?
good energy.
One second, sir. One second. Actually, the voice is not clear.
Yeah, there is a one question in the chat
Am I
box.
audible?
Yes, ma'am. I will share you the book name, sir, after
Hello?
this session. Yes, ma'am.
Sir, in the electron, so there is a spike around magnetic electron volt. Could you just explain what is the reason behind it?
What, ma'am? The Seebeck potential is a
Sir, in the
microelectron volt.
electron,
One second, one second, one second. This one is the hello, ma'am.
reason behind
Where, ma'am? Hello. There's a voltage per Kelvin, ma'am. There's a
it was,
actually there's a
I think, the previous slide.
previous slide. Watt per meter Kelvin second. One by join. हो गया वो राजकुमार? मैं कर रहा हूँ इंडस्ट्री देखो फिर से कर रहा हूँ उसको ज्वाइन करो तो आप करो, एक्सेप्ट करो, एक्सेप्ट कर लो। So I think now we go for the hands-on session. Okay. After that, I will reply. And I'm rewriting my mail. If you have any query, then you just write to me. Okay.
Thank you, sir. Thank you, sir, for this email address.
Now we go for the this hands-on session. Thereafter, I will solve your queries. लो संभालो। हाँ? Yes, yes. Yes, yes. Yes. True, sir.
Hello, good morning all of you. I am audible.
Yes, sir.
Yes, audible.
Let's start to went to using DFT theory, and in the last my guides have a presentation about DFT. Then a basics idea about DFT and how can you use DFT. Then the DFT is very uh, very good tools for study of a band six study, density of state, and electron density. ठीक है. So here in there are various type of software, and we do calculate the density of state, density of band structure, optical properties. But why we have choose to Win2K? Win2K we give a GUI. GUI mean graphical of interference. Here we have can easily without any command, any terminal, we have with the help of the GI, graphical of interference, we can easily calculate because we have a full screen and we have input directly manually. Okay, so let's start DFT. So first, all of you have going to my Mozilla Firefox and DFT. We have used Ubuntu software. Ubuntu, we can say that Linux type my system, then we can easily run the Win2K. Okay. So first we have write in Google search W2 web. Please 1 minute. Wait, sorry for technical issue. Sir, not
किसके के कहाँ जा रहे हो तुम? अरे यार गूगल तो इस पे करता है ना, क्रोम पे।
Mozilla Firefox चलाएंगे Win2K.
क्या चला रहा हो?
वो क्या Win2K.
अरे वो तो W2 क्या लैब पे जाओ ना, नेट नहीं चलेगा ऊपर।
नेट पे चला.
तो ऊपर वो खोलो। अरे ये नहीं बंद कर। अरे वो खोलो ना W2 पे।
हाँ ठीक है. बना सर.
अरे ऊपर से खोलते ना W2 पे।
नहीं तो तुम्हें तो
अरे तो बड़ा
सोच.
तब वो ऐसे भूल जाओ तुम।
Okay, then let's start to W2 web. So firstly we have a command in terminology W2 web. ठीक है. After to W2 web we have a link in this terminology AFM lab 7890. This is a link or we can say ID in the 7890. Sometime sometime happen in the Win2K. Their number can be changed 7890 and a range है उस in between we take a particular number एक ID and we can use the Win2K software. Okay. Then when we have type in W2 web, then we have a link HTTP AFM lab 7890. This is a very this software is licensed software. Then we have a unique ID. Then we have a link. Then we go to this link and we get a interference of W2 web. And this like this type of interference. Welcome to W2 web. So firstly, we have a create a session. Then session name we can create this type. Then now we have calculated the Syria
Hello.
oxide. Then
Hello. Excuse me, sir. Sorry
yes.
to interrupt you, but एट आवर एंड जब हम लोग इसके W2 वेब खोल रहे तब मेरे एंड पे ऐसा नहीं आ रहा है जैसा आपके स्क्रीन पे डिस्प्ले हो रहा है।
एक्चुअली दिस इज अ लाइसेंस सॉफ्टवेयर,
ये सर
आपकी
ये सर
तरफ से
लाइक
नहीं खुलेगा, आपको ये इंस्टॉल करने पड़ेंगे।
यहाँ इंस्टॉल करना पड़ेगा सर हमें पहले, जैसे ये क्या है कि टर्मिनोलॉजी में जाके यहाँ पे पूरे सॉफ्टवेयर को हमें इंस्टॉल करना पड़ता है। उसके बाद फिर ये हमारे पास एक यूनिक आईडी होती है लाइसेंस की। लाइसेंस लेते हैं तो हमें एक नंबर मिलता है 7890। ये में भी चेंज, ये चेंज कब हो सकता है जब हम मल्टीपल अगर इसमें वो रनिंग कर रहे हैं वो क्या बोलते हैं उसको, प्रोग्राम रन करते हैं। जैसे सीरिया ऑक्साइड भी रन करती है, अगर दूसरा करना चाहें, अगर उसको हम एंड नहीं करेंगे, उस फाइल को एग्जिट नहीं करेंगे, तो हमें उसी नंबर पे काम करना पड़ेगा। उसके अलावा
ओके,
हमें
इट
नए
मीन्स
नंबर
कि
पे काम करेगा।
ये ओपन सोर्स नहीं है, ये हम
हाँ,
हाँ
ये
लोग।
ओपन सोर्स।
ओपन सोर्स, ये ओपन सोर्स नहीं, दिस इज ऑल
ओके
ओपन
ओके
सोर्स।
ओके ओके ओके, ठीक है सर, ठीक है। देन वी वुड वॉच ऑन योर स्क्रीन वॉट एवर इज गोइंग ऑन। ओके सर, थैंक यू।
Then we have create a new session. Then we have name any type, but we have our to metal like Syria oxide. We can type their name. After that, type your name. We can click on the create. Then there are several files, but we have new directory create. Then create and change. The new directory is Syria oxide dot and के नाम से हमने new directory create की है, तो यहाँ से हम किस पे create कर देंगे just हाँ नहीं हो रहा, नाम नहीं आ रहा उससे। नाम चेंज कर दो इसको। क्या है कि do not exist। वेट किया है सर, यहाँ पे देखिए सीरिया ऑक्साइड न्यू के नाम से है। कुछ ठीक है. Sorry for technical program, technically Syria oxide to new session, and here we have in the graphical interference we have show the session name, and first off we go to the execution. Execution, the first of struct gen. When we go to struct gen, there in interference we have name has RTCO, I mean Syria oxide. They have lattice parameter and the lattice space group and atoms. So we know that the Syria oxide have two atoms, Syria and oxide. Then and we can use a CI file and put on and upload, and we can also in manually. Then manually is very easy because we have all the input by in the seeing the CF file and can fill the air all the value A, B, C, alpha, beta position and with the calculate the Syria oxide band structure and electron density state. So first of title name Syria oxide, and after the space group, we know that the space group in the with the help of the CF file. So first we have, calculate the national function theory with the help of Venn2K. We have the need as CF file. So CF file Syria oxide we can use the foolproof software also. We can itself create and we download on the database and crystallography database also. There have give information all about A, B, C, alpha, beta, gamma, and a latest parameter is A. In the presentation, my guide have told us the radius in the angstrom also and Boredis also. But here we have used a angstrom. ABC is a lattice parameter because all ABC are equal because we have a cubic Fluoride structure. Then A is equal to B is equal to C. Alpha, beta, gamma is 90-90. We have fill manually, and Syria oxide have and the equivalent atom Syria oxide, we have filled Syria oxide, and the atomic number is 58, and RMT. The main role in this RMT will always equal to and less than 2.3, not more than 2.3 more and 5, but the RMT value different atom and can be different. Okay. The position of Syria is equal to 0, 0. The oxygen position is equal to 0.25, 0.25 and 0.25. These all information we have get the CF file. After this filling this all data can the save the structure click. After that, save the structure. There are several steps: set atomically RMT and continue editing, save file and clean up, continue editing, about editing and restore original file. One by one we have the set these value, and then we go the next step. So first we have set atomically RMT and continue editing value. Then we click here. The RMT will always reduce to more. I am saying that not more than 2, and they may be different for different atoms. Okay. After that, do it, and this last part alternatively we can use it or not, and do it.
Hello,
After
sir.
say yes.
Sir, what is by RMT?
Possible error in the value of ionic radii. If you find the ionic radii value from somewhere, some sites, then you can provide it is plus minus 2% or unlimited 2.0.
Yes.
Yes. So it is a 2% value in the error that can be considered by the software automatically.
Okay, sir. Why you mentioned that range? We have to fix that number.
Actually, when we are relaxing the structure, then we need to know about the ionic radius. So the ionic radius is depending on the coordination number available in the crystal structure. So if the coordination number is 8, coordination number is 6, then there's a change in the ionic radii. That's why here we have provided the RMT value as a 2%. That gives you that our ionic radii can change from 1 to 1.02 to 1.0.098. That's why.
So it is different for different material. RMT value changes.
as well as different materials.
So what is the maximum value for RMT?
You can consider this value of RMT 6, not more
So,
than 6.
It is predefined in app
Yes, it
software.
predefined the Win2K booklet. That there is one booklet is available with the Win2K. They have clearly mentioned that you can go up to 6% of the RMT values.
Sir, what is the basically changes in our calculation? If I change my RMT to 2 to 6%, so what changes I have to change?
As I told you, there is a change in the coordination number. Like if the atom has a coordination number 8, then the ionic radii is, let's suppose, 8 angstrom. If the coordination number is 10, then the ionic radii automatically reduces. That is the
Okay, ionic
6.8 or 7.
radii.
Yes,
Okay.
yes. If you can't get the value of ionic radii more accurately, then you can't relax the structure. That's why we have provided. You can also make it 0. You can
It
make
means
it,
as we increase the RMT values, the ionic radii reduce.
yes.
Okay, sir. Thank you, sir.
Okay. Now, actually, you just note down the several steps in the this process, and if you have any query, you can ask. Okay.
Okay, sir.
Okay.
Sir, you were telling about full proof shooter, that software. So
Full, yes. I am just explaining. Full proof software is the experimental tool software that is based on the XMD data. So here, as you know, no, we have to provide the value of lattice parameter and value of angles. So when you go for the refinement, you can get the exact value of lattice parameter and the angle for your experimentally prepared sample. Okay. जैसे कि
okay,
आप
sir.
अगर
So
कोई
for
experimentally sample, yes, that is another software for the retrieval refinement to
yes, sir.
calculate the more accurate value of lattice parameter and the structure parameter. But that is for the experimentally prepared sample. And here we are using those experimental value to evaluate the theoretical assumptions.
Okay, sir. I understood, sir.
Okay.
Last time I have cleared the first step, set automatically RMT and continue editing. After that we have the second step, save file and clean up. It means हमारे जो फाइल हमने अपलोड किया है वो बिल्कुल सेव है और क्लीन अप करने के लिए हम देखते हैं. Then after that the color has been changed. After that, like this, the all parameter in the last slide is same, but only we have the save and clean up. Okay, and edit the structure, click also, and save structure, and continue editing. Same save and structure every step, and tick. It means for all the 4 steps has been clear. Then save structure. After that, we have a current directory. Let's start ls, and then it means we have a terminology and the program, but यहाँ पे बोल रहा है साइड वाला नहीं आ रहा जहाँ पे बोलते हैं ना क्या बोलते हैं हाँ साइड में वो इसका इंटरफेस नहीं वो नहीं आ रहा जहाँ पे हम आता है तो करने के बाद चलो स्मूथ करे सर वो कहाँ से आएगा वैसे तो इसको रजिस्टर करना पड़ेगा तब आएगा.
Actually, there is a one technical issue with the software. There is a one add-on things are not visible. So I'm just quitting this software and again restart this software so that those options is available. So
because interface is not complete.
Sir, can I ask something?
Yeah, you can
Hello.
ask. Yes, you can ask.
हाँ सर एक्चुअली सर जैसे हम आरएमटी जो रेडियस ऑफ मूवमेंट इन स्फीयर है जो इसकी वैल्यू है
हाँ
तो वो हम चेंज करके रिड्यूस करते रहेंगे चेंज या फिर एक फिक्स रखनी है हमें अराउंड जैसे आपने 2% लिया है
नहीं
इसके अंदर हमारा
we just provide that actually when you perform for the SCF calculation, volume optimization, then
जी जी
we use the RMT values. Okay,
जी जी
only these two calculation.
ओके सर
So initially you can make it 0. If
ओके सर
okay, then you use up to 6% of these RMT values. Because when you use the 0%, then maybe your
जी
structure is not relaxed. That's
ओके
why
सर
we are providing the RMT values to up 2%. That should be, you can just choose from 0 to 6 to any random value. But the maximum possible is 2. Okay.
ओके सर सर जैसे मैं अगर जैसे आई एम यूजिंग द एलिमेंट मटेरियल जैसे मेरा फॉस्फाइड है गैलियम फॉस्फाइड जो ग्रुप 3 फॉस्फाइड्स हैं गैलियम
Yeah.
फॉस्फाइड एल्यूमिनियम फॉस्फाइड इंडियम फॉस्फाइड बोरॉन फॉस्फाइड तो
Okay.
उसके लिए अप्रोक्सीमेटली मुझे कितनी आरएमटी ठीक रहेगी अराउंड
You
कैन
can
आई
use
स्टार्ट विद
2.
द टू
Yes, you start with the 2. If your structure relax, then it is okay. If your structure not relaxed, then either you increase or decrease the value of ionic radius.
ओके सर इट इसका आइडिया हमें जो यूटिलाइजेशन कर्व होगा उससे मिलेगा
हाँ
आफ्टर यूजिंग
तो मैंने आपको कल
आरएमटी
दिखाया था ना कि जो एक वैल्यू लोवेस्ट एनर्जी वैल्यू आनी चाहिए उसमें आपके पूरे कैलकुलेशन में। तो अगर
जी जी
लोवेस्ट
सर
वैल्यू आ जा रही है इट मीन्स कि आपका स्ट्रक्चर रिलैक्स हो गया है। बट अगर लोवेस्ट वैल्यू
ओके
नहीं आ रही है इट मीन्स कि स्ट्रक्चर नॉट रिलैक्स, यू हैव टू चेंज द वैल्यू ऑफ आरएमटी। इसको
ओके सर
रिस्टार्ट इसको रिस्टार्ट करके आओ।
ओके
एक्चुअली वी
ओके ओके
नीड टू
थैंक
रिस्टार्ट द सिस्टम।
ओके सर
बेइज्जती करा
कपड़े देखकर इन्हें पहचाना जा सकता है।
ये आग लगाने वाले कौन है? वो
So actually, these options are not visible at that time. So that's why we have just restarted the system. So now we just continue. So the different types of calculation, AFM calculation, complex calculation, parallel calculation, spin polarized calculation. So here there is execution, there is structure generation, view structure. These options I am talking about, that when you go for the structure generation, then it asks for you the title, whatever the you have sample, then you choose corresponding space group, lattice parameter, the atoms and their position. So if there is a more than one atom is available, then you go for the add an atom and you just put the values of the corresponding atoms. So here the RMT values and this atom coordinate position can be given, and you can also get this information from the literature as well as the little refinement of the software. Okay, so here just you put the value title, whatever you have structure. So let's suppose we are putting here cerium oxide, and the space group are 225, that is FM3M, and this corresponding value of lattice constant. Okay, so you just save structure. As you save structure, then here you go for this RNT calculation, reduce it by that is 2, do it. Okay, yes, save structure, then this, now you just take it.
Start, do it. Screen. Till all the parameters fill cerium oxide. A, B, C, alpha, beta, gamma, and Syria oxide. Here we have fill the Syria oxide, then atomic Z value and atomic R empty value according to Syria oxide. Where we have an other element, for example, अगर if we have put Z value 22, then R empty value 2.19 maybe error plus minus 10, 12. Similarly, oxygen Z, we can see here oxygen atom had Z value 8, but RMT value 1.99. So you can see the difference between RMT value according to Z atomic value of the atoms. Okay? And after that, we have cell structure. Cell structure. Then now we have the file is ready because the color has been changed. After that, the structure then completed. We can the view structure. We know that about Syria oxide structure like fluoride cubic structure. Then we can see easily view structure. Click. Then Excretion software. Excretion software you also install in your Ubuntu and Linux. Then you can easily see. Otherwise, you have Draw and Vesta and other software. But if you have do the structure, you have seen the structure in the your software in the PC, then you are necessary the install the Excretion software, which are the free in this Ubuntu, and we can clearly that the Syria oxide structure like this fluoride cubic structure, and here we have the atom position also. See, and go to file and click here. Display इसका सर वो आइटम दिखा रहे हैं ना नाम and we go to the display and here fourth position atomic symbol. We click the atomic symbol, then we can easily the position of every atom in the fluoride cubic structure, like corners, Syria oxide, and the faces and centered is oxygen. Then you can easily the structure. Now it means our parameters we have filled and the crystal structure is clear and all the parameters are correct. And after that, we have go to initialization calculation. Then initialization calculation have given two system initialization fast mode and individual mode. We can do one anything, anyone. That's we are going to individual mode because we have the manually input in this all the parameter because the nearest distance view output X group they have all the we can check it easily. Then this is very accurately because when we do the individual mode, so first of we X section, then click on the section, then everyone is already filled because we have all the parameter in structure and view structure. Then some value we have can only change. Otherwise, the value has given in this parameter we can execute. Initially, let me continue. After we have view, then we have complete the one parameter, then automatically give the second parameter. Like xnn has been completed. Then we go to view output nn. Then we click the view output nn. Then the all the value, the calculation in the back end using the DFT. तो जो कैलकुलेशन होती है वो बैक एंड में चलती रहती है तो हमें उनको सेव करता रहना पड़ेगा. Save and initially then X group we have click on X group. Initially linear augmented plane we click. We can see easily here. We click on the view output space group. Then the in the listed in found 225 FM3M space group already has written according to software. or we know that we have the fill the first structure, then the space group, we can clearly that 2 to 5 fm 3m. After that we can go to symmetry and calculate the save and initial extract. Here the main point we have always remember the RKMX value. RKMX value vary from 5 to 9. Then we can click here, click in this the blue line, click here for more information. We can click here and we can check it. And they have different from different atom for like helium, the RKMX value 3, lithium 4.5, barium silicon 5, carbon and phosphor 5.5, nitrogen and sulfur 6.0. Then vary 5 to 9. You have clicked the here. For example, this click here for more information. You can check it. They are the value for different atoms. Here we can see that the Syria oxide have RKMX value 8. Then we click here, save and initially. We have clicked on the prepare there. You written in the your run input seems to be kind. You can start initialization. Then now we can initialization, but we have completed all the parameters. View key list also xgen. The decide the number of k points. The k points number vary 500 to 5,000. Then we have 1,000 because not more or not less. 1,000 पॉइंट्स अगर हम लेंगे तो उससे क्या कैलकुलेशन बहुत इजी रहेगी, अगर ज्यादा लेंगे तो उसमें कैलकुलेशन में टाइम लगेगा. दैट्स व्हाई वी हैव लेस नंबर पॉइंट्स. और here shift k max is no, हमें कोई शिफ्ट नहीं दिखना यहाँ पे. एग्जीक्यूट इनिशियलाइजेशन विद save. Here is the perform spin polarization calculation. If we have any material which have the spin calculation, then yes, otherwise no. So here we have not calculated the spin, then no. Then the most important thing in the when to get DFT, first we have any material have calculation, continue with the run as SCF. सबसे पहले हमें इसकी एससीएफ फाइल रन करनी पड़ेगी. अगर एससीएफ फाइल रन करने के बाद ही हम कोई कैलकुलेशन कर पाएंगे, नहीं तो नहीं हो पाएंगे. ठीक है, तो कंटिन्यू विद द रन एससीएफ फाइल. सेव एंड एरर नेम कीवर्ड. ठीक. Here the error name given, we have I think changed the name. Then we can do again structure. If we have name is incorrect, then we cannot run the file. Yes, the session name have same. Uh, Session is RKCO oxide, and here in the home AFM lab we took now same. Then we can easily calculate. Okay. Now this is a clear. Okay. Now we go to view structure. Then display atomic symbol. Then structure is clear. Now we are going to initialization calculation. Then similarly, last time do execute initially lab augmented plane wave, view output, save and initialization, space group. Here the space group is same 225 F3 frame. X symmetry, copy structure, save and initially, extract, execute. Here we can use the select exchange correlation reportation, maybe PBBGGA, LSDA, WCGA, PB sol. You can any potential use as your accuracy and your calculation. So the best potential for calculation PBGGA. So we select the PBGGA, okay, and execute. Continue with initialization login plane wave. Here check RMX value. Save. Yes. Pair. No. Execute. Here we have calculated the Syria oxide for spin or non-spin, spin polarized or non-spin polarized. So we have calculated without spin. Then we have calculated, click on the no. Now continue with the run SF click. Here, these are already data filled according to software. Then you start the SCF cycle. Click on SCF cycle. You can see here the running status. You can running like this color pink and the person are running. So we have can see that the SCF file has run. If the file is completed, then we are going to calculation for density of state, band structure, and electron density, optical properties easily calculate.
So this is the first part of the calculation where you have performed for the several FTF, and this after this calculation, as I already discussed with you, that first you relax the structure, and as the structure is relaxed, then you go for the rest calculation. So I think the calculation is already completed. So here we view. Yes, stop. So if there is a stop, it means your calculation has been done, and then you can go for the rest calculations. Okay. So now I again, Rasmu, just take it.
Calculation, we go to utilities. Here there are several types of utilities, but we are going to task mein we have given the electron density, density of state, and optical properties. After that we go into the volume optimization. देखना पड़ेगा नहीं दिख रहा ये नहीं ये इसके बाद हम क्या करेंगे, वो वॉल्यूम ऑप्टिमाइजेशन के लिए जाएंगे। तो और यहाँ पे देखो सिंगल प्रोग्राम के बाद रहना है, इसके बाद जो एक एक स्टेप छोड़ के वॉल्यूम ऑप्टिमाइजेशन, तो क्लिक है। यहाँ क्यों मिला सर? हाँ लिए भरना पड़ेगा। Click on for volume optimization X optimizer.
2 minutes. I came to lab.
Yeah.
Yeah, because actually issue.
For option 1 to 4, we specify any change according to our convenience. Here we have
That net is not continuously again get now. That meeting, it will not record properly otherwise. That's why. Chalega. I'll come. My laptop.
zero. Yeah. Measure.
आ जाओ कौन है
We have click on the reload in reverse order, click on again and again until C oxide have done the file. Then they have run the optimization job. We can see the here the running and they complete the running the calculation. After that we have the energy float energy curve for volume optimization. In the last slide, sir had discussed about the volume optimization, the minimum energy. At a point, we have calculated the density of state Venn and shown. So that's it. Running on. Always. Here we have again reload and reload reverse order until we have listed this type of burden file deleted over and this whole step. After that, we can see that the running has already stopped. Then it means we have to calculate the complete the process and in the last हाँ तो उस पे आएगा लिखा अपलोड द एनर्जी उस पे लिखा है ना हाँ नहीं सर Now we can plot the graph. ये है ना ये वाला ये वाला ऐसे ये जो पॉइंट्स है ना ये पॉइंट्स है here we can easily see that the stars points are move from high to low and at the 280 they have the minimum energy. So here we have the calculate easily at this minimum energy the Manchester calculate optical properties and electron density.
Excuse me, sir. I have a doubt. सर सर जो ये हमने अभी ग्राफ प्लॉट किया यूटिलाइजेशन कर्व है ना ये शायद
यूटिलिटीज में ये आपका वॉल्यूम ऑप्टिमाइजेशन कर्व है एनर्जी वर्सेस वॉल्यूम
ओके सर इट शुड बी इन द यू शेप और
yes it should be U shape and the data points easily see that clearly see that there's a U shape.
Yes sir. What is
and we have just calculated actually there is a one option is a left during the calculation that's why these data points are now connected in U shape but the experimental data is clearly show that at 280 there is a lowest value of negative value and thereafter there's an increase. So the lowest negative energy value just means that that much energy volume is optimized. So we just calculate the volume of the unit cell is 280 electron cube. 278, not 280. Okay.
Like those rest of state.
Yes. Now one by one we can go for the other calculations. So the most promising thing of the work is that first FCF calculation should be relaxed. If your calculation should be relaxed, then you can easily go for the other rest of the calculation. Okay. So now one by one, as the first task is over, then one by one we go for the another task that is the DOS electron structure. And if the things remains, then we can also show you some another plots of the results.
The edit and RCO, this will file the name, click on this. Save and continue those file. XGen, KMX, they have the Q point already 1000. We have calculated added RKCO. Then we have changed the energy. Energy in the Fermi energy Emax. Then they have given 1.5, I think. 1.5, like we can change for maximum large value. So we have right double 3.0 and save with continuous dose file. And after that in the
Sir, why, sorry to interrupt you, sir, why you double the Fermi energy?
you can change accordingly you 1.5, 3, 2.5 more than or less than.
Actually, the Fermi energy is the middle of the valence band to conduction band. So we have just provided the value which covers the all the bands permissible in the material. That's why we have just doubled. We can also go for the 3 to 4, more than double. You have to put the value here.
Okay, sir.
Okay.
save and continue. Exam. Then they have can the number of point 1500. If we have more than then the running and the calculation have more time. That's why we have less than 500.
These points are not, you can say this will, you must be rigid at this point, but you can also change. Here I want to show you the calculation. So we have taken the some few less number of the K points and the few less number of the band values. But if you want to go for the research publication, you can go above 1000 so that the calculation should be more relevant and accurate. Okay.
Those five.
Sir, in SCA file, you didn't convert the charge. You convert only energy.
We
So
can
it
convert,
is
actually, there are two options. So you can either convert the overall charge or you can convert the minimum value of energy. So
so,
you can go for the both, but here for the Syria oxide samples, we go for the energy conservation.
so it is not necessary to convert both the parameters.
We can actually here most of the property is if you convert the charge, it means the samples has defect free because no rest of the charge is created. But in that case, your material should be like alloy, usually alloy, some ABX2 type materials. For that material, you go for the charge convergence, but for the oxide samples, you can go for the energy convergence. That's right.
Okay, sir. It means oxides can charge only for energy conversion. Energy
Yes,
conversion से काम
for
चल
the
सकता है.
oxide material, but for the oxide halide, you can go for the energy convergence, but you can go for the charge convergence for the alloy samples like ABX2, nickel copper alloy, nickel iron alloy, such type of material go for the
So
charge
I'm
balance.
working on metal oxides. So I'm charge converge both.
You can
So
go for the energy convergence.
it will take more time.
And
So
sir, what
I
about
have
the
to go only for
phosphide?
energy.
Yes, you can go for the energy convergence if your sample is oxide. Because if you know, in the case of the metal oxide sample, there is a permissible formation of the vacancies of the cationic as well as anionic vacancy. Means there is a change in the oxidation states of the metal. But in case of the alloy, that is a nickel copper alloy, nickel iron alloy, there the vacancy is not possible. There should be the balancing in the charge. Like nickel should be present in +2, iron should be present in +3. You can't change the charge. But here in case of oxide, you can change the charge, and due to difference in the charge, you can get the different property.
Okay, thank you, sir.
Okay.
The second step of optional alternative, we can leave because this is optional. The necessary step we have X LAP2 W2. We can go. Then continue with this dose. After that configuration. Here we have more important thing. We have calculate the total density of state. So here this is in the last line. A possible input could look like this is line is written. तो यहाँ पे रखा है कि आपको टोटल डेंसिटी ऑफ स्टेट किस किस की कैलकुलेट करनी है. जैसे वन टोटल उसमें कंप्लीट सीरिया ऑक्साइड का आ जाएगा. अगर आपको डी एफ जी एस पी इनका करना है तो आप उनका भी कर सकते हो. तो हम यहाँ पे लिखने का जो पैटर्न रहेगा जो यहाँ लिख रखा है ऐसे लिखना पड़ेगा हमें. टोटल वन टोटल कोमा like this SPDF. Then we click on this. Then we have calculate one time 5 to 6 density of state at a time calculate. So we have written the total SPDF D1 to G right and in the aggregate. You only one total also SPD. आप SPDF भी लिख सकते हो और उसको भी आप कैलकुलेट कर सकते हो. जो आपको अप्रोप्रिएट है, जो आपको करना अपने जो रिसर्च वर्क के अकॉर्डिंग है, आप वो स्टेट यहाँ पे कैलकुलेट कर सकते हो. एंड एग्जीक्यूट. Now this this all step have completed. अब हम इस नेक्स्ट स्टेट का प्लॉट यहाँ से क्लिक करके देख सकते हैं। तो नेक्स्ट प्लॉट क्लिक, तो यहाँ हम देख सकते हैं कि हमारे पास टोटल डेस्कटॉप स्टेट आ गया है यहाँ पे लिखा हुआ। तो यहाँ से हम इसको सेव, तो यहाँ पे हम देख सकते हैं जो हमें टोटल डेस्कटॉप स्टेट का प्लॉट आया है, वो क्लिक करने से हमें वहाँ हमने पॉइंट पे क्लिक किया तो क्लिक हो गया था। तो ये हमारे पास डेस्कटॉप स्टेट आ गया। ठीक है, वहां पे हमें एक चेंज करना था। जैसे हम वहाँ पे एसपीडीएफ हमने जो पॉइंट लिखे थे, तो उनसे भी हम डेस्कटॉप स्टेट कैलकुलेट कर सकते हैं। ठीक है, तो ये हमारे पास डेस्कटॉप स्टेट ग्राफ आ गए। अब हम दूसरी जो प्रॉपर्टी जो कैलकुलेट कर सकते हैं, जैसे इलेक्ट्रॉन डेंसिटी एंड वेट स्ट्रक्चर। अब हम कैलकुलेट करेंगे बैंड स्ट्रक्चर। कोई भी
एक्सक्यूज मी सर, अगर कंडक्शन बैंड जो है वो फर्मी एनर्जी से आगे जा रहा है तो व्हाट इज द सिग्निफिकेंस ऑफ इट?
अगर आपका कंडक्शन बैंड फर्मी लेवल से तो आगे जाना ही चाहिए। जो नीचे जैसा नेगेटिव वैल्यू है दैट इज द योर वैलेंस बैंड एंड द पॉजिटिव वैल्यू इज द कंडक्शन बैंड।
नो सॉरी सॉरी, मैंने सर रिवर्स बोल दिया। वैलेंस बैंड क्रॉस कर रहा है फर्मी एनर्जी को, तो सर उसका क्या सिग्निफिकेंस है सर?
इसका मतलब कि आपके सैंपल में कुछ डिफेक्ट्स अब प्रेजेंट है पहले से ही, जो भी आपने कैलकुलेशन किया है पोटेंशियल या तो आपका रिलैक्स नहीं कर पाया है, और उसमें आपके डिफेक्ट प्रेजेंट है। वो डिफेक्ट के वजह से आपका फर्मी लेवल जो है वो वैलेंस बैंड के पास शिफ्ट करता हुआ दिखेगा। आपने जैसे सेमीकंडक्टर पढ़ा होगा कि एन टाइप और पी टाइप सेमीकंडक्टर में क्या होता है, फर्मी लेवल जब पी टाइप की डोपिंग करते हैं तो वैलेंस बैंड की तरफ शिफ्ट करता
वैलेंस
है।
बैंड, जी सर।
सो दैट इज सेम कॉन्सेप्ट इज अप्लाई टू एवरीवेयर।
सर अगर डिफेक्ट्स इसमें प्रेजेंट है तो सिस्टम सॉफ्टवेयर में कुछ मिस्टेक करी होगी, या फिर उस वजह से, या फिर पहले से ही डिफेक्ट है?
रिलैक्सिंग की वजह से सैंपल जो है आपका
रिलैक्सिंग
स्ट्रक्चर
की
जो है
वजह से।
रिलैक्स नहीं हो पाया है।
इट
और
मीन्स
अगर आपका यस
एचसीएफ को और हाई कन्वर्जेंस पे रन करने की जरूरत है।
yes you should increase the number of cycles, then you can go for the calculation.
ओके सर, इट मीन्स के पॉइंट्स आल्सो इंक्रीज एंड आरएमटी के मैक्स आल्सो
RMT
7 to 9 पे।
RMT should be also changed. RMT should be also changed at that case.
ओके
But
ओके
in
सर।
case of the oxide, it is I think favorable for your application purpose.
बट सर है ना, उसमें जो डॉस गैप है वो फर्मी एनर्जी से आगे इंक्रीज हो रहा है, तो सर उसका कोई इंटरप्रेट
बट
नहीं कर पा रहा है।
आपको उसको रिप्रेजेंट करना होगा अपने तरीके से। जैसे कई बार कई चीजें होती है निगेटिव, बट उसको आप पॉजिटिव वे में उसको अगर आप रिप्रेजेंट करेंगे तो काफी अच्छी चीजें होंगी वो।
ओके सर।
ओके।
कोई भी हमें इनमें से जो टास्क दिया है, इलेक्ट्रॉन डेंसिटी, डोज, ऑप्टिकल प्रॉपर्टीज, इवेंट स्ट्रक्चर कैलकुलेशन, तो सबसे पहले हमें जो कंप्लीट करना होता है रन एसए फाइल होती है, तो वो हम ऑलरेडी कर चुके हैं। तो उस अब हमें दोबारा करने की जरूरत नहीं है। अगर हम इसको एग्जिट करके दोबारा करेंगे तो हमें दोबारा से फिर जो फाइल है एससे फाइल रन करनी पड़ेगी। तो अभी हमने कोई एग्जिट नहीं किया, तो हम इजीली जो हम कैलकुलेट कर सकते हैं वो बैंड स्ट्रक्चर कैलकुलेट कर सकते हैं। तो वो हम टास्क में जाएंगे तो यहाँ पे हमें सबसे लास्ट में जो बैंड स्ट्रक्चर दिया है उस पर क्लिक कर देंगे, ठीक है। तो बैंड स्ट्रक्चर के बाद यहाँ पे देखो ये जो स्टेप आए हैं हम सभी कंप्लीट करने हैं, तो उसके बाद हम इजीली क्या कर लेंगे, बैंड स्ट्रक्चर कैलकुलेट कर लेंगे। तो यहाँ पे सबसे पहले इन्होंने दिया स्ट्रक्चर एफसीसी। तो हमें पता है कि जो इसकी स्ट्रक्चर होती है वो सीरिया ऑक्साइड की वो एफसीसी होती है, ठीक है। तो उसके बाद क्लिक क्रिएट के लिस्ट बैंड, क्लिक ऑन दिस, कॉपी इट, या फिर हम देखो यहाँ पे दो चीज दी हैं, क्रिएट आर सी के लिस्ट बैंड, और में दिया है जनरेट के मैक्स यूजिंग एक्सक्रीजन। यहाँ पे आप अपने खुद के अकॉर्डिंग भी अपनी के लिस्ट बना सकते हो, बट उसके लिए आपको एक रिसर्च पेपर है वो पढ़ना पड़ेगा, तो उसके हिसाब से बन सकता है। लेकिन ऑलरेडी अगर आप यहाँ पे कर दो क्रिएट के लिस्ट अकॉर्डिंग टू बैंड, तो ऑटोमेटिकली सॉफ्टवेयर अपने हिसाब से के लिस्ट बन जाएगा। जो अभी बैंड के स्ट्रक्चर का जो ग्राफ देखो उसमें नीचे जो वैल्यू आएंगे गामा एक्स वाई जेड, तो वो ऑटोमेटिकली ले लेगा यहाँ से। अगर आप खुद करना चाहोगे तो आप भी बना सकते हो अपने हिसाब से जितने पॉइंट करके करना होता है। तो
सर
यहाँ से हमने क्या किया, क्या मैम?
सर सर जैसे आपने बोला कि यहाँ से अपन एक्सक्रेजन से उसको
हाँ
हाई सिमेट्री पॉइंट लगा सकते हैं। तो सर जो
हाँ
स्ट्रक्चर्स होते हैं सारे क्रिस्टल स्ट्रक्चर उसके जैसे ऑर्थोरोम्बिक है क्यूबिक है, तो उन सबका सेम हाई सिमेट्री पॉइंट होता है या फिर
नहीं
अलग
नहीं,
अलग मटेरियल का हाई
डिफरेंट
सिमेट्री
होगा
पॉइंट
मैम।
अलग है?
हर किसी का डिफरेंट होगा। आप उसमें जो ये केएमएक्स वैल्यू होती है ना आपकी, जो के लिस्ट वैल्यू होती है, तो एक सर से आप कांटेक्ट करने लिए एक रिसर्च पेपर है, तो उसमें सिर्फ दिखाया गया है कि इस मैटर के लिए अगर एफसीसी है तो इस टाइप का हमें की लिस्ट बनाना पड़ेगा, बीसीसी है तो इस टाइप का, सिंपल क्यूबिक है तो इस टाइप का, और एचसीपी है तो इस टाइप का। वहां पे आपको गामा
नहीं,
वैल्यू का अकॉर्ड।
जो
हाँ भाई।
ब्रिलियंट जोन का जो पार्ट होता है वो
हाँ हाँ
आप बता सकते हैं कहाँ से लेना
हाँ हाँ,
होगा
वो
फॉर
उस
जैसे?
पेपर, वो पेपर सेंड कर देंगे हम आपको। सर से कांटेक्ट करना, आप सर के पास है तो उसमें ऑलरेडी दिखाया गया है कि एक पॉइंट होगा मिड पॉइंट, वहां से गामा लेना है, वहां से एम लेना है, वहां से
हाँ,
वाई लेना है,
वही
वहां से
वही
जेड।
मैं पूछूं था, जैसे अगर स्ट्रक्चर चेंज है जैसे क्यूबिक है तो उसके लिए ब्रिलियंट जोन का पाथ चेंज होगा,
हाँ
ऑर्थोरोम्बिक
चेंज
है तो
होगा।
उसके लिए चेंज होगा। तो सर आपके पास कोई ऐसी है पीडीएफ, तो प्लीज सर उसको शेयर कीजिएगा।
हाँ एक जो सर है मेरे गुरु जी हैं, वो मैं उनको बोल दूँ शेयर कर दें। एक पेपर है पर्टिकुलर, उसमें सिर्फ दिया गया है कि आप अगर आपका मेटल की एफसीसी टाइप का है तो यहाँ से यहाँ हम पॉइंट ले सकते हैं, और वो इसमें जो ब्रिलियंट जोन बता रहे हैं उसी हिसाब से दिया गया है, ठीक है मैम।
ठीक है सर। सर उसको मेल आईडी पे जरूर भेजिएगा सर।
हाँ कोई नहीं, सर से आप कर लेना कॉन्टेक्ट।
ओके, ओके सर।
कंटिन्यू विद सर। आप पे हमें वैल्यू चेंज करनी है सर। हेयर भी है तो वैल्यू चेंज फर्मी एनर्जी अकॉर्डिंग टू दिस। चलिए, तो हम यहाँ देख सकते हैं जो हमारे पास जो है, जो सीरिया ऑक्साइड का जो बैंड गैप है, तो इस जो ब्लैक वाला हमारे पास जो लाइन है और इस वाले ब्लैक लाइन है, तो इसके बीच में हमारा 2.2 का डिफरेंस है। तो अप्रोक्सीमेटली जो एक्सपेरिमेंटल वैल्यू होती है उसके कोरस्पॉन्डिंग हमारा जो बैंड स्ट्रेच जो वैल्यू आ रही है वो आ रही है कि 2.2। वैसे जो 2.3 या 2.4 इसकी होती है एक्सपेरिमेंटल वैल्यू, तो नियर अबाउट है, तो इतना थोड़ा जो हमने जो पोटेंशियल लिया था उसके हिसाब से वेरी कर सकता है। जो आप पूछ रहे थे मैम कि जो के वैल्यू होती है, जैसे यहाँ पे डब्ल्यू, एल, लैम्डा, गामा, डेल्टा, एक्स, वाई, जेड, ओमेगा के, ये सब हम इसने ऑटोमेटिक लिया है, सॉफ्टवेयर ने अपने ऑटोमेटिक लिया, क्योंकि हमने वहाँ ब्रिलियंट जोन वाला जो आप बता रहे थे वहां से हम वो खुद भी सिलेक्ट कर सकते हैं, ये कम भी कर सकते हैं और ज्यादा भी कर सकते हैं अकॉर्डिंग टू एक्यूरेसी, जो हम अपने जो उसमें रिजल्ट में एक्यूरेसी लाना चाहें तो उसके हिसाब से कर सकते हैं। ठीक है, तो यहाँ से हमें इजिली हम बैंड स्ट्रक्चर कैलकुलेट कर सकते हैं। तो हमने इलेक्ट्रॉन डेंसिटी कैलकुलेट कर लिया है, सॉरी डेंसिटी ऑफ स्टेट कैलकुलेट हो गया है, बैंड स्ट्रक्चर कैलकुलेट हो गया है। तो अब हम इस पे जाना चाहेंगे, ऑप्टिकल प्रॉपर्टीज हम कैलकुलेट इजिली कर सकते हैं। तो उसके लिए भी हमें ये होता है कि पहले रन जो एस सी फाइल रन करनी होती है, तो वो ऑलरेडी हम कर चुके हैं। यहाँ से इस
Excuse me, sir. I have a question.
हाँ,
Yes, sir. सर जब आपने डेंसिटी ऑफ स्टेट को प्लॉट किया था वो नियर अबाउट द फर्मी लेवल बिल्कुल टच कर रहा था, लेकिन हेयर वी सी द अप्रोक्सीमेट -1 टू बैंड गैप जो हम देख रहे हैं, तो ये क्या कंफर्म कर पा रहा है हमारा बैंड स्ट्रक्चर जो है वो डेंसिटी ऑफ स्टेट को?
But no, actually, at that time, the separation is
Hello.
scale is -5. The scale of -5, -10, -15, -20. But here the scale is 1, 2, 3, 4, 5. So if you see that the separation is here is very small. Hello,
Okay.
am I audible?
Yes, sir. Yes, sir.
तो चूंकि स्केल
Yes,
जितना
sir.
बड़ा करेंगे मैम तो आपको उतना क्लोज दिखेगा, बट जैसे स्केल को आप छोटा करते जाएंगे तो आपको सेपरेशन वहां पे परफेक्टली दिखना शुरू हो जाएगा। हम मतलब यहाँ पे आप देख सकते हैं कि ऊपर आपका जो सेपरेशन है 1 से ज्यादा है, जबकि नीचे 1 से कम है। इट मीन्स कि आपके इस सैंपल में ऑलरेडी पॉजिटिव डिफेक्ट क्रिएटेड है सीरिया ऑक्साइड में। ठीक है मैम।
ओके ओके।
तो इसमें जो बैंड हैं वो किसी भी पैरामीटर में चेंज करके पता किया जा सकता है कि बैंड्स एस के हैं या पी के कौन से हैं या डी के कौन से हैं?
अभी मैम बताया गया था ना, जो टोटल डॉस में वहां पे आप एस पी डी आप वहां पे देख सकते हैं कि किसका कंट्रीब्यूशन कितना है।
वो
तो
तो
जनरली
उसमें बैंड स्ट्रक्चर
इलेक्ट्रॉन
में, बैंड स्ट्रक्चर में जो बैंड्स हैं, जैसे ऊपर किसके मेजोरिटी ज्यादा है, डी के ज्यादा है या फिर एस
हाँ
की
वो
ज्यादा
पूछ
या पी
सकते हैं
की?
मैम, उसको पार्शियल डेंसिटी ऑफ स्टेट बोलते हैं, उसको प्लॉट करके आप देख सकती हैं।
हाँ सर वो
क्योंकि अब
तो
आप हाँ वो पीडॉस है, इसमें भी आप कर सकते हैं मैम कि आपको इंडिविजुअली एटम का सिलेक्शन करके आप देख सकते हैं किसका कंट्रीब्यूशन ज्यादा है किसका कम है।
अच्छा ठीक है।
ठीक, तो कितना ऑप्टिकल करके देखते हैं।
तो हम हमारी जो अब नेक्स्ट जो हम जो कैलकुलेट करें ऑप्टिकल प्रॉपर्टीज कैलकुलेट करते हैं। सिमिलरली इसमें वही होगा, हमें क्या करना पड़ेगा, पहले एस से फाइल रन करनी पड़ेगी, तो वो ऑलरेडी हम रन कर चुके हैं, तो उसका अब हमें रन करने की जरूरत नहीं पड़ेगी, क्योंकि वो अगर हम एग्जिट करते हैं तो रन करना पड़ेगा। ठीक है, तो हाँ ऑप्टिकल प्रॉपर्टीज है टास्क में हम कैलकुलेट करेंगे। तो ऑप्टिकल पे हमने क्लिक किया, तो पहला हमें बार बार क्या है, एडिट टेस्ट इन द, तो इस पे क्लिक करेंगे। सेव एंड कंटिन्यू, यहाँ ऑलरेडी देखो जो हमने फाइल जो लास्ट टाइम यहाँ पे जो चेंज किया था, ई मैक्स मैक्सिमम किया था 1.5 3.0, वो ऑलरेडी यहाँ पे है, तो क्योंकि हमने वहाँ पे सेव कर दिया था, यहाँ पे सेव है, कोई दिक्कत नहीं। ठीक है, तो सेव विद कंटिन्यू ऑप्टिकल प्रॉपर्टीज एक्सजेन, ये सेम वही हमने जैसे यहाँ पे पॉइंट कितने किए थे, यहाँ पे KMX 500, तो वही है। तो इसको हम चेंज भी कर सकते हैं, लेकिन 500 में क्या है कि कैलकुलेशन थोड़ा फास्ट हो जाएगी और जल्दी हो जाएगी, तो टाइम सेविंग है। लेकिन आप एक्यूरेसी के लिए करना चाहोगे तो इसको 5000 तक ले सकते हो। यस, एक्जीक्यूट, continuous optical properties. तो देख सकते हैं हम यहाँ पे हमारे पास जो ऑप्टिकल प्रॉपर्टीज का जो ग्राफ आ गया है, ठीक है। यहाँ से हम इसको सेव भी कर सकते हैं, सेव एलईपी ऑप्टिक्स, तो हमारे पास वहाँ पे सेव हो जाएगा, ठीक है। तो ये हमारे पास ऑप्टिकल प्रॉपर्टीज का जो ग्राफ आया, हम देख सकते हैं एक्सपेरिमेंटल भी करेंगे तो हमारा ग्राफ इस टाइप का ही आएगा, ठीक है। तो वहां से हमारा कंफर्मेशन हो जाएगा कि जो वैल्यू है वो सेम है। 60 हमें अगर इसको अपलोड कर रहे हैं, जैसे इसको हमें ये क्या है कि हम जब यहाँ इसको हमने अपलोड किया है तो इजीली यहाँ से अपलोड हो गया है, ठीक है। तो ये एक इस मतलब सॉफ्टवेयर इमेज है, सॉफ्टवेयर ने अपलोड किया है। अगर आप खुद भी इसको अगर अपलोड करना चाहते हो तो यहाँ से जाओगे बैक करने के बाद, तो यहाँ पे जो ये वैल्यू है ब्लू कलर में RKC लोस लेप्सन, तो इन पे क्लिक करोगे डाउनलोड होकर इनको देखो। तो यहाँ डाउनलोड करोगे तो हमारे पास इसकी वैल्यू आ जाएगी लाइक दिस। इससे भी फाइल डाउनलोड करके आप देख सकते हो, तो इसमें आपको डेटा मिलेगा, तो इससे आप अपना जो ग्राफ खुद, हाँ ये आ गया यहाँ पे। तो यहाँ पे जो वैल्यू है देखो, एनर्जी है, रियल पार्ट ऑफ एक्सेस है, इमेजरी पार्ट ऑफ एक्सेस एक्स एक्स है, रियल पार्ट ऑफ जेड जेड है, और इन एप्सिलॉन जेड जेड है। तो यहाँ से आप एनर्जी और रियल पार्ट के बीच में ग्राफ प्लॉट कर सकते हो, ठीक है। तो ये अपना खुद आप ओरिजिनल पे भी कर सकते हो, और ये प्लॉट यहाँ पे इन्होंने दिखा भी रखा है, जैसे यहाँ पे सॉफ्टवेयर ने भी अपने आपको ये प्लॉट दिखाया हुआ है। तो आप दोनों में आपको जो सही लगे वो कर सकते हो। सिमिलरली इस टाइप का ग्राफ प्लॉट करेंगे जब हम यहाँ पे रियल जो वर्टिकली है वहां पे हम रियल पार्ट ले लें, और जो ओरिजिनल है वहां पे एनर्जी लेके इस ग्राफ को प्लॉट कर सकते हैं, ठीक है। तो हमारा ग्राफ आ जाएगा। तो यही थी हम जो कैलकुलेशन कर सकते हैं, इलेक्ट्रॉन डेंसिटी, ऑप्टिकल प्रॉपर्टीज, बैंड स्ट्रक्चर, तो ये सब हम इससे इजीली कैलकुलेट कर सकते हैं। हो गया। हाँ,
इसको
ठीक।
डाउनलोड कैसे करेंगे इस इमेज को?
क्या हम इमेज को तो यहाँ से डाउनलोड हो जाएगा, राइट क्लिक करेंगे ना, तो देखो ये सेव इमेज है, कॉपी इमेज है। तो उससे
तो
अच्छा
ये
है कि आप जैसे मैं
डाउनलोड हार्ड कॉपी इन पोस्ट स्क्रिप्ट ऑप्शन आ रहा है, अगर
इस
यहाँ
पे
से डाउनलोड।
यहाँ से क्लिक करके अगर हो जाए तो ठीक है, यहाँ से हो जाएगी, हाँ ये हो गया।
अच्छा
बट
सर।
बट ये होगा ये कि ये देखो आपने देखा किस फॉर्मेट में, ये PS फॉर्मेट में है, ठीक है। हो सकता है आपके उसमें मतलब ओपन हो ना हो लैपटॉप में, अगर हो जाए तो अच्छी बात, आप इसको पेस्ट कर सकते हो। और जो मैंने दिखाया पीछे, जो ब्लू लाइन में जितने भी वो पॉइंट थे उन्हें आप देख लेना, उसमें सब वैल्यू दिए हैं। आप ओरिजिन
तो
पे जाके
उसमें
इसको पूरी,
राइट क्लिक करके वो डाउनलोड हो जाती है?
हाँ हाँ वो भी हो जाएगा। नहीं वो अगर आप पॉइंट से अगर प्लॉट करना चाहो तो खुद भी कर सकते हो उससे।
हाँ सर, उन्हीं का पूछ रही थी सर।
हाँ
उसमें
तो उनसे
एब्जॉर्प्शन कोएफिशिएंट, एप्सिलॉन, रियल डाइलेक्ट्रिक और ये सारी चीजें मिल जाएंगी ना सर?
हाँ हाँ वो सारी वैल्यू उसमें दे रखी है, आप उससे प्लॉट कर लोगे इजीली।
ओके ओके सर।
सर एक क्वेश्चन था।
हाँ हाँ
सर जब हम ये, जैसे आपने अभी ऑक्साइड का एक मटेरियल लेके देखा आपने, सीरियम ऑक्साइड समथिंग, अगर हम इसी चीज के अंदर अगर आगे जाते हैं क्वाटरनरी या फिर टर्नरी कंपाउंड्स की तरफ, देन तो हम किस तरह से करेंगे इसको? क्या हम स्टार्टिंग में जब हमने HCF साइकिल वगैरह रन किया था उसमें हमारा ऐड एटम का ऑप्शन था, क्या वहां से ऐड करेंगे या फिर कोई और ऑप्शन होता है?
यस 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 यस, अगर यहाँ पे जैसे यहाँ पर अगर स्टेडियम ऑक्सीजन दो एटम है, तुमने दो एटम ऐड किया, बट अगर आपके किसी कंपोजिशन में मान लीजिए कि मोर देन 5 atoms है, then you just go for add an atom and corresponding Weikart position and atomic coordinate.
ओके सर, वन मोर
Yes yes
डाउट।
yes.
सर एक, जैसे कि मान लो हम क्वाटरनरी पे और हम टर्नरी कंपाउंड्स की तरफ गए, अगर हमारा कोई ऐसा हम कंपाउंड बनाते हैं जो हमारी मैग्नेटिक प्रॉपर्टीज भी शो करता है,
Yes.
then is it possible to calculate the magnetic properties also from this Win2K code?
Yes. I have already shown you my in my PPT. There is a magnetic susceptibility. So
Okay.
using Win2K, you can also calculate magnetic susceptibility, and also you can calculate by considering the individual spin polarization. You can spin magnetic moment. You can also calculate.
ओके सर।
Okay.
सर आप
Actually, we are
अपनी जो
working.
पीपीटी
I'm
में
working on
आप,
the oxide materials, perovskites materials. So we are and DMS, dilute magnetic semiconductor, but not the purely magnetism, where we are using the iron, nickel, copper, cobalt. But we are using by this transition metal, we are using it as a dopant, so that we can just tune the magnetism in the oxide samples.
ओके सर।
Okay.
Sir, we
Yes.
can apply Hubbard parameter in Win2K, and
Yes,
is
you
the
can.
same
Yes,
process?
you can. Yes, you can apply Hubbard parameter also.
सर जब मैंने
Yes.
अपने मेटल ऑक्साइड्स को इसमें फीड किया था, तो सर उसमें नंबर ऑफ एटम ज्यादा थे, तो
अच्छा.
वो स्ट्रक्चर जैन बन नहीं रहा था। तो सर उसको सिफ फाइल के थ्रू Win2K में ला सकते हैं?
हाँ, CIF फाइल अगर आपने रिफाइनमेंट उसका किया है आपने, तो यू कैन डायरेक्टली इंपोर्ट CIF फाइल टू द this software. But instead of importing, because the format of the CIF file in different software is different, so it is not necessary that your prepared CIF file is directly imported. So instead of importing, you can just go for, I'm just showing you, uh, you just go
तो
for
सिफ
COD.
फाइल में भी डिफेक्ट प्रेजेंट्स होते हैं, हो सकता
Yes
है
ma'am.
उसमें भी इम्प्योर। ओके
Yes ma'am.
सर।
Yes ma'am. You can go for the COD database, and here you can search for your desired material, and you can get easily information about the structural parameters from this website.
सर सिफ फाइल में, जैसे मैंने एक COD से सिफ फाइल डाउनलोड करी थी, तो उसमें एक मेटल के लिए, मटेरियल के लिए सूडो पोटेंशियल जो होता है वो डिफाइन नहीं कर रखा था, उसको ब्लैंक कर रखा था। तो सर उसको फिर कैसे
ये
फीड किया जाएगा?
आपको विंटूके में कोई भी सूडो पोटेंशियल आपको फीड नहीं करना है। इसमें
नहीं सर,
क्या है
ओनली फॉर
कि
सिफ फाइल।
yes, you just import the zip file, and based on the zip file, they can easily suggest you whatever they can take the exchange potential.
ओके सर।
Actually, this is the just quality of the Win2K. You can just calculate the band structure, band related properties, and the software directly calculate based on the structure, atoms, and their spins.
ओके सर।
If you have any query further, I have already mentioned my mail in the chat box. You can mail me your query. Okay.
सर
ओके सर।
जैसे कि हम
हाँ.
कैलकुलेशन करते हैं, अगर हम इसमें 1D तक जाते हैं,
Okay.
1 डायमेंशनल तक, देन ये Win2K कोड को हम डायरेक्टली यूज करके अपने लैपटॉप में
नहीं, आप
सोल्व आउट कर
इसको
सकते हैं?
एक्चुअली इसका बल्क तक और 2D, आई मीन 2D मटेरियल तक यूज कर सकते हैं। 1D के लिए आपको, चूंकि पोटेंशियल उसके लिए डिफरेंट हो जाता है वन डायमेंशनल केस में,
तो उसके लिए
आपको ये
क्लस्टर्स वगैरह
सॉफ्टवेयर,
का यूज कर रहे हैं, क्लस्टर वगैरह की जरूरत पड़ेगी उसके लिए।
हाँ, उसमें आपको क्लस्टर की जरूरत पड़ेगी और मे बी आपको हाई स्पीड कंप्यूटर सिस्टम की जरूरत पड़ेगी। या तो सर्वर अगर आपके पास है तो सर्वर बेटर है आपके पास।
ओके ओके सर।
Actually, we have just started the DFT from the last 1 year. I think one of my friend, that is Sanjay ji, he last year joined our institute as a DST Stuti
Sir,
DST department.
can I ask a personal question from
Yeah,
which
yeah, you
institute?
can ask. Yes,
सर आप कौन से इंस्टीट्यूट से हैं?
मैं ट्रिपल आईटी इलाहाबाद से हूँ, इंडियन इंस्टीट्यूट ऑफ इंफॉर्मेशन टेक्नोलॉजी इलाहाबाद।
इलाहाबाद। ओके सर,
Yes.
थैंक यू।
Okay. So I think this much is enough for today because there is a time limitation. So the rest of the things will be, I think, take care by the rest speakers.
Sir, I have one question actually.
Yes, yes, you
This
can ask.
sample we have unknown sample actually we don't know that value of the we are giving some value actually we before programming
Actually,
actually
there is a one research article, and I will share this research article with the AIP members, and they can easily share with you.
oh,
Okay.
oh.
Look, so Sanjay ji, any other? Yes.
Yes, sir. So thank you very much, sir, Upendra sir, for your hands-on training as well as for giving the theoretical background about the DFT. I hope most of the doubt of the participant might be clear. There is a very good interactive session also there. So I thank once again Dr. Upendra sir for his lecture.
Okay.
Now let us go
Thank
to
you.
the next. Now let us
Yes.
go to the next lecture. It will be given by the Kausal sir. So
Okay. So thank you so much, participants, for listening me. Okay. There might be some issues. You can just mail me your queries, then I can resolve it.
thank you, sir. Thank you, sir, for your
Okay.
answer.
Thank you, everyone.
Thank you, sir. It was a great session.
Thank you, ma'am.
Thank you very much, sir. Thank you.
Thank you, sir.
So next, let us call the next speaker. That is Kausal. So Kausal Ageda is an assistant professor in the Department of Applied Physics, the Maharaja Siaji Rao University of Barodara, Gujarat. Sir is also working on, sir has an research interest in liquid dielectrics, nanoparticle synthesis, luminescence, dye absorptions, theoretical condensed matter, and he has very good knowledge in these systems. And Kausal sir is presently an associate chief editor of the AIP bulletin. So Kausal sir, please start your presentation, your lecture.
Thank you so much, sir, for the great introduction. Let us start. I think it will be a kind of a fun uh, because so let us discuss about Orca. So Orca is a very user friendly and I think it's easier than the Burite. Okay, so and its speed you can say that its timing for the calculation is very fast and we will get kind of very good output from this software. Okay, so let us start. Mm, let me share my screen. Okay, is it visible for you?
Yeah.
Yes, sir. Your PPT is visible.
Okay, okay, okay. So let us start. Density functional theory through ORCA. Uh, so today's outline. Okay, 1 second. Yes. Today's outline is the installation of Avogadro Orca version, basic tools of the Avogadro, because Avogadro is a kind of a visualization software, and also it's making an input file for the Orca. Okay, so I am just so more time will be spent in kind of Avogadro software, because it's a very easy, and even it's a input to file maker. Okay, then after construction of material, uh, you can construct any type of material, liquid, solid, even liquid crystal. Okay, so I will show you kind of my recent work, okay, in liquid crystal also. So then after the generate input file for the Orca, optimization, single point energy. So we can also find out IR spectra, or you can say that FTIR spectra from this Orca, Raman spectra, UV visible spectra. Okay, and find out a band gap and a band gap from the UV visible spectra. Okay, also we can explore NMR, EPR, fluorescence, and phosphorescence spectra. Okay, so this much I can I do my best for the completing all the task for today's lecture. Let us see. Okay, I think participants install or Avogadro. Yes or no? Have you
Yes, sir.
installed or not?
Yes, sir. I have installed it. Yes, sir.
Okay, okay, good, good, good.
Yes, sir.
Please,
I have also installed.
yes, please write on the chat box. So I just aware of this. Okay, how many people's uh, with me? Okay,
Mm.
for the
Kaushal sir, most of the students are saying yes in the chat
okay,
box.
okay, 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 okay.
Uh,
Uh, so
there are two participants who are saying they could not install it.
okay, so kindly go through the uh, WhatsApp group, and there I have kind of message, or you can say that I sent this install version of the Avogadro. Okay, so I think first part will be done. Yes. So basic tools. So there is a kind of a different kind of tools: draw tools, navigation tools, manipulation tool, selection tool, auto rotation, auto optimization, click to measure, align molecules. Let us see. So open. 1 second. Yes.
Sir, it can be installed in Windows.
Yes, yes, yes. You can install in Windows as well as kind of Linux also.
Okay.
Yeah. So you can see that there is a screen, or there is a Avogadro, okay, software. So let us understand what is a first is a draw tool. So these you can see that a pencil kind of this. So this is a draw tool. Just click on it, okay, and select whatever element you have required. Okay, so let me show you. The select carbon. Okay, bond order is a single, and here adjust hydrogen. It means that like whenever I right click over here, okay, so you can see that there is a 4 hydrogen is automatically coming. Okay, uh let me click on the label, then you can see that. Okay, you can see that is a center one is a yes, the center one is a carbon, and another is a hydro. There are four hydrogen connected to the carbon, and that is a methane. Yes, exactly. Okay, just okay. So सबने सब मेरे साथ ही कर रहे हैं ना? Have you done like this using kind of a draw tool? Okay, okay, good, 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 good. If you have any query, okay, just uh, feel free to ask. Okay, yes. So
जी
right
सर
click on the center and वो click जो है
सर
वो आप
where is
sorry
sir
sorry
where is draw tool sir after
okay okay
installing
okay
what
okay
we need to open
just open Avogadro software. Okay, you can see
yes
kind of
yes yes
like this, and this is the first you can see that a pencil symbol.
okay
Okay, click on it and just right click on the black region. Okay,
I'm not getting sir
not getting.
I am getting, but structure it is not coming actually.
Sorry.
All option I am getting actually. Whatever option is there, the label and carbon
Okay.
dipole like this I am not getting, but the
Okay.
pencil.
Okay. Okay. So you are getting methane or not?
No, no, sir. No,
Sorry.
no, sir. Actually,
No. So just click on the draw tool. Okay, and right click on the sorry, not a right click, left click. Okay, so regular click. Now, is it clear or not?
If you're facing a problem, I also face that problem. So can you close and restart? Then it might work.
now, sir, I got.
Okay, okay, okay. Good, good, good. So, okay. Then if you have a right click on the carbon atom, okay, so it's remove. Okay, वो remove हो जाएगा यहाँ से अगर right click किया तो, ठीक है? Okay. So again, just click on it background, sorry, black region, and just click on the carbon atom and drag it kind of this. So you can see that these uh, these ethane, okay, CH3. You can see that. Okay, have you done? So yes, okay, okay. Rina says yes. Manish, yes. Okay, Lipsa, Nanda, yes. Okay, good, good, good. Okay, okay. Let's go further. So, if you click on the bond, okay, if you click on the bond, so it is convert into a double bond. Okay. Okay, good. So let's go further. Again, if you remove the bond, then right click on the bond. Sorry. Yes. So again, click. Then it's a three bond, I think. Let me check. Yes, is a three bond. Okay. C triple bond C. sorry, CH triple bond CH, kind of this. And again you have click, sorry, then it convert into the single bond. Okay, so let me repeat. Okay, just click on the bond. Yes, from drawing pencil, yes. Okay, again click, it's convert into the 3 bond. Okay, triple bond. Again, if you click, then it's convert to the 1 bond, single bond. Okay.
Also, sir, please tell them how to zoom in and how to zoom out.
Okay, okay, okay. So zoom in and zoom out for the your scroll down and scroll up. Okay. It is very similar like your image. Okay, if you have image, then if you zoom it, then just scroll down and scroll up. Okay. So let me show you the second navigation tool. Okay, just click on it and you can see that it is rotating. Just click and rotate your mouse. Okay, rotate your cursor. Then it's moving. Okay, then you can check that my atom or my molecules will be perfect or not. Okay, sometime it's happened, then there are if there are many atoms, then one or two atom it is not there, so you can easily check from the 3D. Okay, okay, let us check. Okay, navigation tool, and then after manipulation tool. Okay, yes, manipulation tool. So from this manipulation tool, it is not like it's very important tool, but you can see here, you can see here, you can translate by from the x-axis, from the y-axis, from the z-axis, and rotate from the x-axis, y-axis, and z-axis. Okay, but it is very easy from this navigation tool, so you cannot. Okay, so it don't I think it's needed. Let us see another tool. Selection tool. Okay, so from the selection tool you can select one atom or many, kind of this. Okay, and select, and even also control plus C, you can copy and you can paste. Okay, from the another Avogadro kind of this. Just let me show you, let me show you. So select all and copy, and I have a second screen. I have a second screen for the Avogadro. Okay, and just paste over here. Then you can see that, you can see that it is a pasted. Okay, it's a copy, and you can even also drag and put it any kind of this. Okay, yes. So it is a selection tool, then auto rotation tool. So from the auto rotation tool, select none. You can just select none, then it's going to be a वापस उसी फॉर्म में आ जाएगा जिस फॉर्म में हमने रखा था. ठीक है. So from the x-axis you can see that, okay, This is the auto rotate tool. This is just rotating in the x axis. Okay, let me stop. So I just set y direction, and you can see that. Okay. If you guys any query or any problem, then feel free to ask. Okay. So there is a kind of this. Okay. Uh, yes. So let me show you this auto optimization tool. So in this Avogadro software, it is a very interesting kind of tool. It is a auto optimization tool. Okay, so in any DFT software, you must need a optimization first. Okay, so in Burai, okay, where is that rotation option? Okay, so this kind of yeah, you can see that over here, auto rotation tool. Okay, just click on it. And you can see that here x y z axis, and just rotate like this and start, then it's rotate. Okay, okay, let me go ahead. So don't put it on the message, just uh, unmute yourself and speak. Okay, yeah. So in any DFT code or in any DFT software, first we have to optimize that particular any molecule or any structure. Okay, then and then you can find out a minimum energy and a kind of band structure and all this. Okay, so in Avogadro software there is again kind of auto optimization tool. Over here, you can see that a force field is a UFF. Also, there is a different kind of a force field over here. If you need any kind of or if you require any kind of force field, you can just select it. So just I am just selecting a universal force field. Okay, step per update 4, it's enough, and we are not changing over here, and just start. Okay, so you can see that here auto optimization E is equal to kind of energy, and here DE means that energy change is zero. Okay, energy change is zero, and you can see that here a bond length is also a decreasing. Okay, it means that it's this structure is now optimized. This structure is now optimized. Okay, just stop over here, and you can just go further. Okay, तो ये प्रोसेस सबने सबको हो गई या फिर बाकी है, मुझे बताइए.
ये सर हो गया.
If you try kind of another molecules, you can, you can just, you can see that. So this is a methanol. Okay, so this is a ethanol, and again this is a propanol. So this structure is kind of this, but it is not optimized. Okay, it is not a stable structure. So again, we have to use kind of this tool, auto optimization tool, and start. And you can see that uh, over here, it's calculating energy difference. Okay, it is up to a kind of 10 raised to 8 or 10 raised to minus 9. Yes, it's 10 raised to minus 9, and now this structure, it's optimized. Okay, yeah, you can say that the structure is now optimized. Okay, yeah. So if you have any problem during the optimization, or if you have not understand how to
So,
use this,
yeah. So
yes,
what is this field? This
sorry.
force field and all, there are like we have different options for force field.
Yes, yes. So force field is also defined from the different potential, So in the literature, you can find out that force field or potential, what they kind of use. Okay, but it is just again I am using, so I will use Orca. Okay, for the optimization. Again, we are doing the same kind of, but it is in DFT software. This is not a DFT software. This is just a kind of you can say that visualization software. Okay, so we can say that it is not actual, maybe. Okay, maybe. Okay, because optimization is, you can say that it's it means that minimum energy. Okay, so minimum energy in which state? Okay, so there is a various state over here, but in that particular minimum energy, okay, minimum energy we can get, it is true or maybe it's not true. Okay, so this just I just show you how to use this visualization software Avogadro. Okay, let me show you kind of okay, let's just go through. Okay, auto and click to measure. Yes, click to measure. So you can see that click to measure tool. Okay, just in that particular tool, we just calculating a bond length. Okay, it is a very important again for the structural information of the molecules or of the structure. Okay, just click on it. You can see that kind of star kind of this thing. Okay, and again I just click on C1, and you can see that it's a distance is 1.531 angstrom. Okay, so we get distance between a C1 to C2 atom. That is, again, it's a very important tool. Okay, again you have to click on the C3, and you can get angle between A1 between A1 sorry, C1, C2 and C3. Okay, so how much angle making in between the kind of a C2. Okay, so it is also 33.9 degree. Okay, I think it is not okay. Yes, here. Yes. So again, I click on H7, and you can see that it is information for the dihedral. Yeah, you can see that. Okay. So we can also find out a dihedral, even angle, and even a distance between two atoms from this tool. Okay. So after optimization, we will getting kind of this distance, angle, and dihedral. Have you done or not?
Sir, in my case, left side display type, why I am not getting? I am getting structure everything. Display type, axis, ball and stick here, like dipole force, like this. Display type, I am not getting in mind here. Any
Display
option?
type. Okay. In where? Okay. Okay. It's display type. Okay. So you have to kind of display setting.
Okay.
Okay. Just click on it and you
Okay, sir.
get it.
Okay,
Okay.
sir. Thank you, sir.
Okay. Okay.
Okay, sir.
Yes.
Now,
Okay. But if you have done kind of this click to measure tool or not, because it is also important. Okay, participant, have you done or
Sir,
not?
I'm not getting the bond angle and distance.
Okay. Okay. Okay.
I have clicked on the icon, but I am not getting it.
Icon. Okay. Icon means this click to measure, na?
Yes, sir. This one.
Okay, okay.
Yeah,
So
yes,
you
sir.
have construct kind of this molecule or not?
Yes, sir. Yes, sir.
Okay,
A different
okay,
one, but yes.
okay. No problem, no problem. So just 1 second. Mm,
Nothing is being displayed at the lower end of the screen. Like it's displayed in your screen now.
okay, okay. Yes. So just click on the any atom, one atom. Just
Okay.
simple click.
It's still not showing.
Oh, I think just 1 second. You just close this software and again restart. Okay, reopen
Okay.
and construct a molecule and just check. I think it is. दूसरे किसी को ऐसा कुछ प्रॉब्लम है क्या? Okay. I was able to follow all the steps till now. Okay, good, Manish. So, Mohini,
Yes, sir.
so have you done or not?
Sir, I made the molecule again, but it's still not showing. I will try later. It's okay. You can continue.
Okay, okay. So all this tool is there. Let me go further. Construction of material and build. Okay. So let me just okay. So this fourth option is a build. I think you can see. Then you can insert. Okay, so there is a four option: DNA, RNA, fragment, smellies, and peptide. Okay, just click on this. Sorry. Click on the fragment. Okay, just see the box. Okay, so if you have kind of required aromatic material, just double click on it and you can see that all this kind of material is already there. Okay, aromatic materials. So let me show you. Just click on the anisole and insert button. Okay, you can see that okay, just navigation tool, click on the navigation tool and check it. Okay, so uh, please go through the select option and select none. Then you can see that there is a aromatic uh, material anisole and you can get from this build option, from the build option. Okay, so it is a very a big library, you can see that. Okay, so all type of material are there. Okay, it's a ligand and ether and cyclic sugar and all this. Okay, even in alcohol, alkane and alkene and amide and amine and amino acid and aromatic and all this. Okay.
Are all these names only IUP synonym, right?
Yes, yes, yes. I think it's okay. Yeah.
Yeah, because sometimes what we know common names.
Yes, 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 exactly, exactly. So it is not here, right over here, methane. Okay, so any kind of a common name, you can say that. Yes, we cannot find a common name. Yeah. So let me show you. Okay. Just Control A, press Control A and select and just delete. Okay. So you can also kind of a selection, okay, of the all this. Yes. Okay. Once again, click on the this draw tool, adjust hydrogen, click over here. Then you can see that it is just carbon atom. It is just carbon atom. Then go through the build, and now let me show you how to build a supercell. Or so first I just show you how to just make a nanotube. Okay. So 1 second. Yes. So you can see that. Let me select and select none and label off. Okay, and just you can see that there is a carbon nanotube. Okay, so it is a very useful whatever you are if you are doing in nanotube and all this. Okay, you can rotate and check.
Sir, how did you do that? I mean, how you extended this?
Okay, let me show you again. Click on the draw. And click on the adjust hydrogen. Okay, so we are getting only a carbon atom. Just build, click on the build option or build and just nanotube builder, and you can see that over here in the bottom of this software you can see that n is equal to 2, m is equal to 4, length is 4, periodic unit. Okay, cap with hydrogen, yes or no. Find a double bond. Okay, so if you have required this kind of, just change it and just build.
What are sir N and M options?
So it is I think it is just shape kind of this. You can see that there is a different angle. It's you can see that it's adjusting in different angle. So I think it is a N and M. You can adjust and you can get a different shape of the nanotube. Okay. Yes. So let me delete. Again. I think it is. Yes. Click on the again carbon atom. Okay. Build. I think a supercell builder is not working on this particular in single atom. Okay, so you have to require just CIF file. CIF file. Let me show you. Let me show you. Just open and in the my download in the downloading in download just I have a NaCl CIF file. Okay, this is I so this I got it from the material project. Okay, just click on it and just open, and we can see that these kind of NaCl structure, NaCl structure. Okay, here you can see that ABC, okay, cell parameter, and it is an angle between them, alpha, beta, and gamma. So this is a cubic structure. This is a cubic structure of the NaCl. NaCl. This is a cell parameter. You can see that over here, and this is a atom. Okay, you can also change. You can change. Okay, if you have a kind of a doping problem, okay, you are working on the doping problem. Okay, so in the NaCl we are doping kind of calcium in terms of in instead of Na, just backspace over here, delete it, and just write down a Ca. Okay, and apply. Then you can see that these changing. This is a changing. Okay, from the Na to Ca. Okay, sodium to calcium. Okay, so this is how we can dope. Okay, so this is a doping problem where, so if you are working on the doping and all this, so you can easily change, but you have to know about how much percentage are you doping. Then you have to calculate all this thing, and then you just uh, kind of this shape. Okay, let me show you different thing. Yes, again, go to the build, supercell builder, and you can see that over here, A repeat, B repeat, C repeat. Okay, so in x-axis, how many times you are repeating this cell. Okay, to making a supercell. Okay, so just write down over here 2 and generate cell. I think yes. So software is not working properly. It's okay. Yeah, you can see that. Okay, you can see that this is making a supercell. Okay, so this blue kind of atom, let me show you label. Yes, so this again it's problematic. This is not A5 but it is an A. Okay, sodium atom, and this is a Cl. This is a Cl. So you can also do it like this. Okay, you can make a supercell from this Avogadro software. Okay, so
Sir,
यहाँ
where
तक.
can I get these
Sorry,
CIF files for
sorry,
different crystals?
sorry.
Where can I get CIF files? This
Okay,
you have
okay. I
provided
think I
this
think
file
Deepak
for
sir.
NSL.
I think yes. I think Deepak sir show you. Let me show you again. So this is a material project site. Okay.
Okay.
Okay. Let me back. Yes. So I am finding a NaCl structure. Just search it, and you are getting this option. I am click over here, and you are getting this kind of. Okay, and just export as CIF symmetry and find out and just downloading it. Okay, and you are also using COD kind of thing. Okay, I think Upendra sir is also told you same thing.
Yes, I can share the link in the group of COD.
Okay. Yes, so it is I think it is. Yes, one thing is also a remaining. You just go through the view property, view, and just go to the property and just select the atom property, and you can see that element name, type, valence, formal charge, partial charge, X, Y, and Z. Okay, X, Y, and Z. These kind of, you can see that this is atom property. Okay, you will getting kind of this. So we have kind of 32 atom. Okay, in this structure. So we can also kind of, okay, just close again, view property and bond property. So it is no bond over here. It's no bond over here. So let me let me construct mm, and view again property and bond property, and you can see that mm, okay, you can see that it's a CC bond. So starting bond is a C1. So it is a name C1 and C2. Bond order is a 1. Rotate is no. And length is, so bond length is 1.822 angstrom. Okay. So over here a CH bond, C1 and H1, C1 and H1. You can see that C1 and H1. Okay, and the start atom and atom bond order, rotate no, it is not rotatable, and the length is 1.07. Okay, so you can also find out the bond property over here. Yes, let me show you another property. Now, angle property. Yes, so you can see that so angle between these three, start atom C2, vertex, it means in between C1, and atom is H1, and angle is 109 point something degree. Okay, so you can also find out this kind of angle property through this software. Okay. I think also it's remaining torsion property. Yes. So it is also a torsion degree over here at CCH. Okay. First atom, second atom, third, and fourth. Yeah. Again, conformer property. It is not our kind of using. Yes. If you have any query, please ask.
What is saying about liquid crystal, some measurement or something in PPT. So,
sorry.
Some liquid crystal molecule actually drawing purpose.
Okay. Okay. So I told you, just I am showing you 1 second. Yes, you can see that there is a liquid crystal. I don't know its name, but I just recently, uh, 1 second. So I just recently doing the research on it, and not research, but I just doing a DFT on it. Okay, one of my collaborator, okay, doing this synthesis of this liquid crystal, and just I am doing a DFT on it, and you can see that there is a liquid crystal. I think atom number is let me show you how many atoms in that. So it's a 58 atoms. Okay, So in DFT, it's a very huge number. Okay, 58 number atom. Okay, so it's very huge, and I think in conventional DFT, you are getting kind of 3 to 4 day to optimize it. Huh? Just optimize it. Okay, but in this Orca, in this Orca, I just show you a output file again. You can see that this is doing in just 3 minutes. So it is a very fast. You can say that the Orca is very fast compared to the Quantum Expresso, even Win2K, even Gaussian and all this, Gaussian and all this. Okay, so so it is very quick and fast. But I am also using the kind of, once again I just show you. Okay. So it's a 74 atom, huh? It's a 74. No, it's not 74. I just show you another thing. So I am working on the workstation, but it's just have a 12 core, not more than. Okay, 12 or 24 core, nothing else. Okay, nothing more than. So it is a very quick. Okay, and finding out just homo lumo thing, and it is very useful. You can see that. So this blue region is showing presence of the electron. Sorry, it's a positive ions, and red region is showing that negative electron region. Okay, and this is a lumo. This is a homo, and you can see that. Okay, and in many structure or in many kind of molecules, this homo lumo gap is the same as a band gap. Is the same as a band. Okay, so you can also find out a band gap from this. Yes, so there is a visualization software. Let me do the running process. Second, I think I have to close it. Yes. So I think open. Just construct this ethanol, sorry, ethane. Okay, and extension over here, Orca, and generate a Orca input file. So this is a very important thing. So now we are just doing making an input file for the Orca. Okay, for the Orca. Let us see. So in basic option, there is some calculation. So in calculation option, there is a three option: single point energy, geometry optimization, and frequency. Okay, so in geometry optimization is a must. Okay, if you are not doing optimization, your calculation is wrong, totally wrong. Okay, so first you have to optimize this, okay, through this Orca, not Avogadro software. Okay, so there is a two thing. uh, so first you have to click on the geometry optimization method. So calculating this four, you can calculate through this four method. RHF means restricted Hartree Fock. Okay, DFT, MP2. I think MP2 is a maybe it's a perturbation kind of this thing. I don't know. It's a very its actual meaning. Let me show. Let me see. Kind of. Yes, yes. So you can see that MP2 is a second order molar palisade perturbation theory. Okay. You can also use this method. CCSD, couple cluster single and double theory. Okay, so you can also uh, calculate this uh, through this four method. Okay, RHF, DFT, MP2, and CCSD. Okay, but just for this uh, in this session, we are just using DFT over here. Okay, so your format of this XYZ axis is a Cartesian. Okay, always do it. Okay, keep it in Cartesian. Basis side, it's okay. Now let me go ahead through the advanced level. Okay, so in advanced level basis set, you just put it any choose any four. Okay, so this last one is a very accurate one, but for the time consuming and all this, just select first one, DEF2 SVP. Okay, then again go through the control. In control, you just click on the DFT method and run type. So what is your run type? What you are required? So we are requiring geometry optimization. Click on it. Okay, you change a multiplicity and also a charge, but we are not doing it over here. Okay, uh, then go through the SCF kind of this accuracy. So extreme SCF, very tight and normal. So if you click on the extreme SCF, your time will be increased. Okay, and similar like this, and just select normal. Maximum SCF step, we don't know how much iteration going on this structure. Okay, so put it over here. A maximum iteration is 999. Okay, SCF type, we just always select restricted, not unrestricted, and restricted open cell. We are not using these two. Okay, if you are requiring, then you can. Okay, but we just select restricted. Converger. So these two option are there, DIS IS and KDIIS. Let me show you in my PPT. One second. Yes. Huh. So converger is a DIS. It means that a direct inversion in iterative subspace, and KDIIS is for alternate algorithm. Okay, so in many structure you can just change DISS to KDISS. Okay, and observe the difference between these two. Okay, which one is good for your structure. So it is also a kind of observation and research kind of this. Okay, and the second order, it means SOSCF, it means approximation. Second order SCF, and NRSCF, it means that Newton Raphson SCF. Okay, let me back to this. Okay, so just select DISS and the second order SOS. Okay, just click on DFT. So here is a grid. So in quantum expresso, there is a K point and all this. Okay, but here you can see that four. Just we are just putting over here four. Final grid is a default. Ha, yes. So this is the main thing. So in DFT itself, various kind of a functional, and you can see that LDA, BP, BL, YP, PW91, B3 LYP, B3 PW. Okay, so all these, even in Orca, there is just it is not Orca software, it is Avogadro software. So that's why it's kind of limited functional over here. But you can just go through the Orca manual and find out many DFT functional. Okay, over there. Okay, just selecting this B3 LYP because it's very advanced and it's good. But again, It is your structure. If you using a different structure, just check different functional and see that what is the difference between these two. Okay. If you are getting a minimum energy from this any one functional, so this is the best for your structure. Okay. Yes. uh, Up to this, it is clear or not? Up to this, sir, DFT option is not showing for me. uh, I think it is not possible. बेसिक में आपने यहाँ पे DFT किया था क्या?
For me as well, it is not showing, sir.
Okay. Okay. So first, just follow me. A calculation, geometry optimization method is DFT, and a format is Cartesian. Okay. Just go through the advanced level. Okay. In advanced, there is a basis set, there is a control, there is a SCF, and there is a DFT. DFT option not showing for me as well. I don't know. Same here. Okay. Sneha is not getting. You get?
Yeah, I can
Are you
see.
are you getting or not?
Yes, yes. I can see
Okay.
the option.
Okay. Okay. So I think just again you just close your software and again reopen.
Sir, if in control method we click DFT, then we can get the option.
Okay. Okay. You are not. Okay. Okay. Yes. Yes.
They
Yes.
might have not picked the DFT. That's why
Yes.
they are
Yes.
not
Yes.
getting the
Yes.
option.
Yes. Yes. Over here, you just click on a DFT. Yes. 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 Okay. Then showing option over here. Now it is clear or not? Yes. Good. Okay. Okay. Okay.
Sir, just shows from starting, just from starting.
From the starting.
Just
Basic or basic or in advanced?
sir, first which option you press? Actually, you got basic, advanced.
No, no. Basic or advanced?
No,
Yeah,
no,
yeah,
first,
both.
sir, we got the table in basic and advanced option is there, na? From which option we get go in? That which option on the software?
Okay, okay. You are just just click on the D control and DFT. Then you are getting DFT over here.
No, he's asking from where you get this window.
Where
This
you
auto
okay, okay,
paragraph.
okay, 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 okay. Let me show you again. Extension. Okay. In extension, it's Orca and generate Orca input.
Okay, okay, sir. Now
Done? Okay. Let me check. Okay, it is as it is. SCF is as it is. TFT is also as it is, and just do it B3LYP. Data. Okay. So in data, if you are it is not required for the optimization, but when we are doing kind of 1 second. Yes, when we are doing a single point energy, and then after you just click amos and basis set. Okay, then you can get a homo and lumo structure for for your structure. Okay. So in this optimization, it is not required. Okay. Just generate, click on the generate. You are getting this box kind of this DFT. So if you have any just save on the desktop. Okay, so you are getting easily. And please make sure that your structure is not big because takes take a time. Okay. Yes. Now just file name 2.inp and save. Okay, and I think it is yes, save over here. I just delete it. So if you have getting or not this up to this, are you making or not input file? Okay, Rena says yes. Okay, Manish, yes. Okay, good. Lispa, yes. I think. Okay, good, good, good. So let me just check again. Okay. Just open it. Okay, and you have to delete all these three, all these two. Sorry, from your input because you downloaded I think Orca 5 for Aishwarya. Okay, so you are I think you downloaded maybe Orca version of 5. Okay, but this input file is for the version 4. Okay, Orca 4, 4.2.1 something. Okay, so for the Orca 5 you have to delete these two. Again I am just showing the normal print and grid 4, just delete it. Okay, and this it is also you can delete, and control S, then this file is saved. Okay, you can see that B3LYP is your functional OPT, it means that optimization process. DEF2 dash HVP is your basis set, and DEF2 slash J is also basis set. Okay, normal SEF because we are not kind of high level SEF. Okay, या फिर high accuracy SEF. Yes, just close it. And write down a CMD over here. CMD, command prompt. I think it's a C user and admin. ऐसा लिखा होगा सब में. Okay. Just write down over here a CD space desktop, because you are just downloading. Okay, sorry, you are making your input file over here, that's why. Okay, but in my case just enter, and in my case I just making a DFT folder. Okay, enter. Yes, yes, write down Orca over here. If you have installed Orca, then just जो भी आउटपुट आएगा वो ऐसा आएगा कि दिस प्रोग्राम रिक्वायर द नेम ऑफ पैरामीटर फाइल एज आर्गुमेंट फॉर example orca test.inp. Okay, if you are not install Orca, then you are not getting this command. Okay, understand?
Okay.
Okay. So let
So
me.
if we have not installed Orca,
Yes.
then we cannot execute this optimization.
Yes, 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 yes. You cannot execute. Okay. So if you have a downloaded or Orca, then you can. Okay. Yes. So write down over here Orca. Your input file name is 2.inp space greater than sign. You have to write down your output file name 2.out and just enter. And you can see that uh, this blink it over here. It means that process is running. Okay. Also, if you check your file, so many file over here, so many file over here. Okay. So it is running. It takes some 2 or 3 minutes maybe. So this is the simplest code. Yes. So it's done. It's done. No. Yes, it's blinking. So it is also. Yes. Now it's done. Now it's done. You can see that this much file you are getting from this software. Okay. So this is your input file and this is your output file. Just double click on it. Okay. And you are getting this output file. Okay. Yes. So it's take I think 1 minute and 9 seconds. Close it and again open your Avogadro because now we are analyzing output. Okay. Now we are analyzing output. Just delete it and again open whatever you are doing this and just click on the output file because there are various files, but you have to make sure that it's output file and open. Okay. So this is your output. Okay, this is your output. So this is optimization. On this we are doing just optimization. Okay. Now, so यहाँ तक clear है क्या? Have
Sir,
you done?
what optimization we are doing?
What optimization means?
That means bond length or I am not getting optimization.
So optimization means that it's itself kind of changing bond length and angle and all this and showing the minimum energy. Okay, showing a minimum energy.
Okay, sir.
Okay, so first step is clear.
If we have downloaded the CIF file
Yes. Okay.
from sources, then
Okay.
Uh, it will be already optimized, na?
No,
Do we
it is
need
not
to
optimized. No, 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 it is not optimized. It is not optimized.
And
Okay.
do we need some kind of suppose we have synthesized some material
Mm-hmm.
and what we can do if the CIF file is not available online?
Okay, okay, okay. Good question. So you have to just draw over here. Okay, but because it is not another way to construct the molecules or your structure, but it is not possible that it's totally new structure. Okay. If you are doing any doing on the material, so it is just first it's available material, then you are doing the doping and all this and making a new material. Am I right or not? Yes. Okay. So
Yes.
that's why you are base file you can download from the material project, and then you can doping, okay, and making a new material, okay, and then you can do the same DFT. Okay.
Suppose I have downloaded a save file and open here,
Hmm.
and suppose I want to change some part.
Yes,
Uh,
yes, you can.
so means I can change atoms in that, right?
Okay.
Okay.
So I already mentioned, I already shown you that NaCl kind of structure, and just changing Na to Ca, okay, sodium to calcium, okay,
Okay. Right.
okay. So that's uh, you can change. Okay. So first step is clear, or first step is over. Now let's do the second step. Mm, okay. Just extension, go through the extension, orca, generate orca input. Okay. Now we are calculate single point energy, or you can say that a minimum energy. Okay. Just select method on the DFT, nothing else to be changed. In advance, basis set, okay, control, you have to select DFT. We are also run type is a single point energy, because we are just doing a single point energy. SCF, put it over here 999. All thing is same. Then DFT, you just change your B3LYP. Okay, in data. Now we are just click on AMOS and basis set, and you can see that this access code, or you can say that syntax is over here. Okay, this is for the finding out a homo lumo, and from the homo lumo you can find out 11 electrochemical property. 11. Okay, I'm just showing uh, which one is that. Okay. Mm, just completing this generate button. Again, you have to change your input file name, because it is a second portion, or you are now doing a single point energy. Okay, then just save. Okay, 1 second. Okay, now you can see that my input file is generated. Let me show this two thing is deleted, and this is also okay. Now you can see that this is the extra portion. Okay, for the amos means that molecular orbit. Okay, just save it, and my file is ready to run. Cancel. Again, open your CMD. Right over here, orca 3 point, because my input name is 3.inp greater than sign 3.out. Just click on enter, and it's running. Let wait for output. Oh, so it's very quick. It's done, because you have already optimized this system or structure. That's why. Let me open again. Open. 3 output. Yes. Okay, so now you can see that from the right hand side, this orbital, and we are also getting energy and symmetry. Okay. Mm, just scroll down, and click on the LUMO portion, and you can see that, one second. Yes, this is a structure. Okay, this is a LUMO structure and this is a HOMO structure. And what is a HOMO and LUMO? Basically, it is a lower unoccupied molecular orbit, and HOMO is means that a higher orbit occupied molecular orbit. Okay, so just check it over here. A difference between these two. Here, LUMO energy is a 1.788 electron volt, and HOMO is a minus 9.189. Okay, so this is a structure for the HOMO. Okay, so you are getting these two value, HOMO and LUMO. Let me check. I think I have mm, kind of paper over here or not. So you can see that. So I think I am not getting put it over here. All this kind of chemical electrochemical properties, but you can find out. Yes, you can see that energy gap, electronegativity, electron affinity, softness of the material, chemical potential of the material, ionization potential, hardness, global electrophilicity index, and it is not, I think, one second. Another paper. Okay. Yes, now you can see that almost kind of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this 11 property you are getting, and 11 property is over here. I think almost is same: electronegativity, electron affinity, softness, chemical potential, ionization potential, hardness, global electrophilicity index, optical softness, maximum charge transfer index, and nucleophilicity philicity index. Okay, so you can calculate from this two, only these two parameter, E homo and E lumo. It is a energy of homo and it's a energy of lumo. So from these two parameter, you are getting kind of 11 chemical property, electrochemical property. Okay, for this. Okay, I am working on. So one of my collaborator Naveen is working on a DMF and hexanol. It's a liquid. Okay, so it's binary liquid. So I'm doing this. Okay, yeah. Also, it is homolumo is homolumo gap is kind of uh, state that or indicate that a stability or reactivity of the material. Okay, so pharmaceutical people and even chemistry people is also requiring this kind of this thing. Okay, so that's why homolumo is a very important for the uh, research. Okay, yes. Are you getting or not?
Yes, sir.
Okay. Any other? Manish, Sneha, Mohini.
Yes, sir.
Okay. So you are doing the same
But
or
to a certain
different?
extent, but
Sorry, sorry.
I need to revisit these recordings. But to a certain extent, yes.
Okay. So you are doing with me or not?
Yes, I was doing, but in the meanwhile, I got stuck. But later on, yes, I will
Okay.
visit
Okay.
it.
Okay.
But yes,
Good.
it seems that it can be done. I can do it because the
Okay.
explanation which you have done is very, very crystal clear. It is.
Okay.
Yes.
Okay. Thank you. uh, okay. Let me go ahead. Uh, Let me check FTR spectra. Okay. For this structure. Remember this thing, if you have experimental proof, okay, then you can compare this, because in many research paper, I'm just publishing, or I'm just putting in pipeline. Okay, so many reviewer ask why you are doing, or why you are comparing experimental FTIR and theoretical FTIR spectra. Okay, so because if you are comparing and your result is nearer, okay, for the experimental and theoretical, then you can say that my optimization is right, or it's true, or my structure is optimized, well optimized, and uh, my lumo energy and homo energy is accurate, because I am just getting same kind of this thing. Okay. Yes, Manish say that yes, doing it, but got stuck earlier, not able to keep track, but it can be done. Okay. Okay.
It seems my messages are having a time lag.
Okay, okay, no problem, no problem. Yeah. So that's why you can say that from the homo lumo you can get 11 electrochemical property, and it's a physical meaning of it, obviously. Then you can search in Google Scholar, you can get all the physical meaning of the 11 property, and you can apply on your research, and make it your research, I think, next level. Okay, go to the next level by using this homo lumo only. Okay, so let me show this the third step. So we are just covering a second step, because the first step is the optimization of the structure. Second step is finding out a single point energy. Okay, single point energy. One second, I am just showing your my output file. No, this is not. No. So one second. DFT workshop, and okay, output file. Yes, so in my output file, you can see that dipole moment over here. Yes, dipole moment over here. Okay, and this structure have zero dipole moment in debay. Okay, so you can also find out a dipole moment from this, and you can see that your final single point energy is this, but it is in Hartree. Just aware of it, not in read band, not in electron volt, and not in another any other unit, but it is in Hartree, capital E small h. Okay, so you have to convert if you are required. Okay, so this is your final single point energy from this output file. Sorry, if you have any doubt, please ask, and if you are not, please mute yourself. Okay. Okay, so you are also getting a mere population analysis. Okay, so this is also an important thing. You can, I'm not covering a theory over here, because I'm just showing a hands-on. Okay, so you just remember this thing, mere population analysis, and you can also put in your research paper. So this is again reach your research. This is a load in population analysis. Okay, you can also put there. Okay, and Mulligan population analysis. This is my, I think this is a famous one. Okay, Mulligan population. If you are doing a research on a theoretical one, so this is I think it's important for you. Okay, let me close. Let me just extend again and going through the third step. Yes, you can, please.
Yes, these all results are calculated assuming that the temperature is 0 Kelvin, right?
No, 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 no. I think I'm just showing no. So it is in third step. You can I am just showing. I will show a kind of temperature. It's a 25 degrees Celsius.
Okay, so
So you are absolutely right. It is not a conventional DFT. Okay, it is not conventional DFT, but its result is very much nearer to the DFT. Okay, yes, it's a part of DFT, but again, it's not a 0 Celsius calculation. Okay.
okay, because I thought if we have to compare it with experimental,
Hmm.
we need to look at the temperature part.
Yes, 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 yes. Absolutely, absolutely. So again, in FTIR, I will show you temperature is 25 degrees Celsius. Okay, in output file. Okay. Yeah. So just click on the generate. Now you have to choose over here a frequency. Okay. Method is DFT. In advance, as it is single point energy to change the frequency. Over here is a DFT. SCF. I think it's okay. DFT and just changing this functional. Sorry, data. We are not click on this and generate. So it's a 4. Save, and we are getting kind of this file, input file. Okay. Again, go through the command prompt. Okay. Uh, just write down capital O small r C A space 4 dot IMP space uh, 1 second. Please share this recorded video. Yes, you can. You will get. But if you are a Windows user, then it is very easy for you. Okay, with respect to any other, I think. Okay. 4 dot out. 1 second. I just forgot to delete because it's going to be error. Okay. Okay. Now enter, and it's running. Wait 2 or 3 minutes. Sir, why Orca installation is necessary to execute the file in Avogadro? Why Orca installation is necessary to execute the file in Avogadro? Because you cannot have visualization without this Avogadro. Okay. Yes, Dr. Jitendra.
Orca can also be installed on Windows 10, or it is only suited,
Yes, why not?
Windows 11. Okay, sir.
It is also you can install in Mac and Linux.
Okay, sir. So it is always free or some limited times trial version is available?
No, it's a totally open source software. Okay,
Okay,
and
sir.
it's a similar of Gaussian. Okay, it's the same as
I'm
a
getting idea
Gaussian.
of Gaussian.
Yes.
So, thank you, sir.
So it's completed.
Hello, sir.
Huh.
Sir, this software is only for molecules only. Shall I use this for like transition metals and nanomaterials?
Yes, you can. But remember one thing, you have a workstation. Okay,
Oh,
then and then you can run. Okay, but without workstation, it is not, or it's takes so much time. Okay,
okay.
so now I'm getting in this point. Uh, I am just running in the uh, series kind of this. Okay, it is not a parallel run. Okay, it is not parallel run. And how to do the parallel run, I just show you. But first of all, let me analyze our result. Okay, sorry. Open 4O. Okay, now you can see that. Now you can see that. 1 second. I just. Hmm. Now you can see that kind of vibrational, wave vector over here, and this is the intensity. This is the intensity. Okay. Let me show you. Yes, and start animation. Now you can see that it's a very funny thing. Okay, so it's uh, vibrating kind of CH bond. Okay, and I think 3000 centimeter inverse, it is represent a CH bond. Okay, stretching CH bond. Okay. Mm, Again, let me show you. 1 second. This point two. Now you can see that. So it is not now stretch. It's now rotating. Okay. It's also a different type of this. Yeah. Okay. You can see that. Okay. Stop animation. And now click on the show spectra. And you can see that this is the same as the experimental one. Experimental one. Okay. This is a wave number on the x-axis, and in y-axis is the intensity. Okay. So you can get the frequency spectra, or you can say that FTIR spectra over here, for this structure, Okay. And आपको ऐसा लग रहा है कि ये रिजल्ट बहुत डिफर कर रहा है, almost 100 to 200 centimeter inverse. Okay, then you have to choose kind of tight SCF. Okay, because you have to increase your accuracy level. Okay, from this. 1 second. Extension orca in advanced level. Control your yes, accuracy you have to go through tight SCF या फिर very tight. Okay, if you are requiring more accuracy, then you can go through it. And my personal experience is that experimental result and theoretical result is almost vary by 20 centimeter inverse. 20 to 30. I think more than 50, not more than 50 centimeter inverse. Okay. So delta V, okay, delta V or changing of wave vector is kind of or wave it's kind of 50, around 50, not more than that. Okay, so it is quite good. It is quite good because it is a theoretical one, and we are just comparing to the experimental result. Okay. Yes. Mm, okay. Let me show you again. Yes, you can please.
In the second step, we found homo and lumo energies.
Yes.
But this is for organic materials. For
Mm,
semiconductors, we get valence band and conduction band. So,
okay.
can we get such energies? I mean, we can get energies in form of HOMO and LUMO, but they are actually valence band, conduction band. Is it
Okay.
right?
Yes, is it exactly right? Okay.
Okay.
If you doing in metal kind of this, so I think अब देखो ये सॉफ्टवेयर है, सॉफ्टवेयर को पता नहीं है कि ये मेटल है या फिर सेमीकंडक्टर है। ठीक है, वो बता तो देगा एक बार। ठीक है कि इतनी इसकी होमो है और इसकी इसका एनर्जी होमो एनर्जी इतनी है और लूमो एनर्जी इतनी है। ठीक है, वो बता तो देगा, लेकिन अगेन आपको आपके रिक्वायरमेंट क्या है उस हिसाब से आपको देखना पड़ेगा। ओके।
Okay. Thank you.
Yes. Okay, let me show you output file of this. So in this frequency output file, you are getting kind of 1 second. Okay, you are getting Gibbs free energy. Okay, Gibbs free energy, and also entropy, enthalpy. Okay, so this is entropy, and it is in EH. EH means that heart rate. Huh? Remember this thing. And enthalpy. Okay, so enthalpy is over here minus, and it's thermal energy. So you are getting also a thermodynamic property from this frequency calculation. Frequency calculation. Okay. So this is very important, and okay, I think it is not okay. Mm, yes. So you can see that thermochemistry at 298.15 Kelvin. Okay, you can, now it's clear. So it is running
Yes.
kind of 25 degrees Celsius.
Right. Right.
Okay. Yes. Mm, okay. Let me close. Hmm. So for the frequency, you just change over here OPT frequency FREQ and go ahead. For the Raman spectra, you just edit this syntax in your input file. Okay, so for the beginner, you can use Avogadro to making kind of input file of the Orca. But if you are familiar, then you can directly change your syntax on the input file, and you can get various result. Okay, Raman spectra UV visible. So for the UV visible, you just doing edit this three thing percentage TDDFT. TDDFT, it means that time dependent DFT. Okay, en route it's 30. It means that it shows kind of 30 energy level. And so this is a syntax. It's a part of syntax. Okay, and you can get U visible spectra. So other spectra you can also we can get from the other NMR, EPR, spin orbit coupling, fluorescent and phosphorescence. Okay, you can also see that documentation and manual for the Orca. Okay, so I think it's done. Thank you so much for the listening me and your kind support. Thank you so much once again.
I have one more question.
Yes, please ask.
Yeah, so you just showed that command lines for UV spectra. Where to write those lines? Yeah.
Yes. Okay. Good question. Uh, you just open your input file. Okay.
Okay.
So now your XYZ, it means that the position of your atom is same. Okay. In all the calculation. Okay. Then you just change over here only. Okay. Nothing else.
Okay.
Because it is not a part of this input file. It is a kind of data file, a data of the your position, sorry, position data uh, of the atoms. So remaining is this, and I am just writing over here this much portion
Okay.
in
Got
all.
it.
Okay, so it is very simple, I think. And if you have any kind of problem to doing this mm, or doing this all the spectra and all this calculation, you can contact me, okay, through email and even also my mobile number. I will provide you. Okay. So
Sir, I
if you
have
have
small.
any query, please ask.
Sir, I have
So
small
can we
doubt
calculate
because
the mechanical properties under different temperature and pressure conditions of any crystal? Suppose you have taken the example of NaCl, and can we calculate the mechanical property under different temperature and pressure conditions using this software?
So I think this orca is like ocean. Okay. So ये समुद्र जैसा है.
Then
मैंने
we have
just
to explore.
इतना ही explore
Okay.
किया है. So you have to go, you just go through the orca manual, uh, search it, and you can do yourself. Because mechanical property, or you can say the elastic one and all this. So I am not aware of it, or I am not explore till now. Okay, so you have to explore, and you are not getting any video of the orca. Okay. So it is because it's very I think it's very new, not new, but people not aware of this software. Yes, Jitendra. Dr. Jitendra.
Okay, sir. Thank you. Sir, thank
Okay, if you have any question, please ask, because it's interaction section, maybe.
sir, I have small doubt that you are saying about the fluorescence phosphorescence.
Yes,
So
yes,
you
yes.
think that what you want to show in the picture or what you want to?
It's
I am
a
not getting
image,
actually.
image.
But
You are,
how?
yes, okay. Similar like this. 1 second. Similar like this. You just extension over here, and just click on the spectra. Uh, Here you are getting kind of another option. Okay, just click on it and showing the spectra. Nothing else.
Sir, fluorescence and phosphorescence spectra we will get.
Yes, 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 yes.
Okay, okay. I thought that whatever image you are making, that image maybe fluorescence image, phosphorescence.
Uh, no, no, no. You are just getting a spectra over here, because in 1 second I just show you. Mm, Manual allow. So it's a 1000 page. Just finding out. So there is a very huge kind of this. So you have to explore this and 1 second. Yes. So this is 8.2, 8.21.3. Okay. You are getting like this. Okay. You understand this?
Sir, I understand.
Okay.
Another,
Yes. Please.
sir, another thing, can I know that, sir, what you are working actually? That means you are making a designing of a compound and you are giving to that another sir, and he will make that whatever property you are expecting, that property he is getting or not in liquid crystal.
In liquid crystal, in liquid also you can find out from the simple structure. Okay, NaCl and all this. So I'm just showing 1 second. CaO structure. If I have, yes, I have. Okay, 1 second. So recently we just you can see that. So there is a CaO. Okay, is a CaO structure. So in some structure, there is a kinding of problem of not showing a proper bond. Okay, so you can easily you can do from yourself. Okay, just selecting oxygen. Okay, and just okay. Now you can see that these sorry, these a cubic structure. Okay, for the CaO, calcium oxide. Okay, and there is a kind of a 4 CaO. Okay, so I'm just now working on it, the synthesis of the CaO, and doing photosynthesis, and not actually photosynthesis, but kind of dye absorption through the calcium oxide nanoparticle and all.
Photocatalysis, right, sir?
Yes. One so thank you for remind me. I just show you one thing. No. So it is very amazing thing. You can see that. So this is a dye. Okay, it's a methylene orange dye. Okay, and upper one is that it's a copper nanoparticle. Copper nanoparticle. So this image for the after optimization image. Okay, and you can see that I think bond is bond is okay. Yeah, you can see that this is bonding. Okay, so it's absorption over here. Absorption over here. Okay, and once again you can see that this is a benzene ring. Okay, so here is a double bond, but here is not. So it's also a breaking a bond. Okay. So you can just imagine kind of this. Okay. And there is a methylene orange dye. It's lower one. Okay. And upper one is that a copper nanoparticle. I think it is a FCC structure, or I don't know exactly, but look at this.
Yeah, it's FCC.
Yes.
सर एक मेरा क्वेरी है
Please, sir.
ये जो ये एक मिथिलीन ग्रुप है और ये कॉपर है, ये डाई डिग्रेडेशन से कर रहा है क्या? ऐसा कुछ
ऐसा क्या?
ये डाई डिग्रेडेशन से करा रहा है क्या? आर यू शोइंग द केमिकल मैकेनिज्म?
No, I cannot showing, but yes, I can predict from the this electrochemical property, because we are getting a homolumo energy, and from the homolumo energy we are getting 11 properties. Okay, and then you can say that my electron affinity is this much. That's why you can say that degradation is there and all this. And also
इसका मतलब ये है कि जो हमारे जो केमिकल है, जैसे
हम्म,
कॉपर के साथ अटैच, मतलब कौन सी जगह पे अटैच होंगे,
yes,
प्रेडिक्ट
yes.
कर रहा है क्या?
But again it's a so much kind of kind of a structure. If I just put it over this die, put it over inside. Okay. Okay. So this atom is affected, this side atom is affected. If I put a cross, you can say that क्रॉस, इसका मतलब कि मैंने अगर मान लो कि कॉपर पार्टिकल को रखा है, उसके एग्जैक्ट 45 डिग्री पे मैंने डाई रखी है। ठीक है, तो ये वाले जो आइटम होंगे वो अफेक्ट होंगे। सो इट इज सो मच काइंड ऑफ यू कैन जस्ट
नहीं,
चेंजिंग।
मेरा इंटरेस्ट ये थी कि हम लोग गैस सेंसिंग में जो काम करते हैं,
ओके
तो जैसे मान के चलो कॉपर थिन फिल्म है, ठीक है ना,
ओके
कि
ओके।
उसमें यदि हम एमोनिया गैस को सेंस करना है,
हम्म
तो वो कैसे एमोनिया गैस उसमें अटैच हो रहा है, क्या ऐसा मतलब कि अटैच कहाँ पे होंगे, क्या इसको प्रेडिक्ट कर सकते हैं?
प्रेडिक्ट कर सकते ना, क्यों नहीं कर सकते?
अच्छा अच्छा,
वी
वही
कैन
मैं
वी
जानना चाह
कैन
रहा हूँ।
वी कैन वी कैन
ठीक।
because we are so from the visualization you can see that, because you can see that over here there is a three bond for the copper and a methylene orange. Okay, but also you can predict from the homolumo energy. Okay, so this much electron is transfer, okay, or not transferring, or attraction and repulsion and all this. There is there is a very various kind of 11 property, then you can easily explore over there.
हम आगे काम करेंगे कोलैबोरेटिव इन गैस सेंसर।
बिल्कुल सर, बिल्कुल।
ठीक।
So if you have
Sir,
any doubt
sir, I have a doubt, sir.
okay, please.
Sir, while we doing composites and all, suppose V2O5 RGO composite, we have to show the channeling of electrons to the RGO sheet, right, sir? So can we do with the help of this software, sir?
So I think you are telling that I have a one sheet and I have some another material over there. Okay, am I right?
Yes, sir.
ओके, एंड ये चार्ज सॉरी इलेक्ट्रॉन क्या ट्रांसफर हो रहा है नहीं वो देखना है ना?
Yes, I want to visualize the channeling of electrons through from the from the V2O5 or V3O7 to this sheet.
Okay, visualization. Okay, so you just so one second, I just show you another thing.
Sir, also how these free radicals are acting on the dye, that kind of its visualization also. Uh, I was asking whether it is possible.
No, I'm not getting your point.
Sir, while the metal oxide is degrading the dye,
Okay.
these free radicals are formed, right, sir? OH free radical and O2 minus free radicals are formed. So
Okay.
those free radicals will degrade the dye. So visualizing those things, is it possible? I was asking. And the other thing,
Yes. Visualization is possible. So this is a trajectory XYZ file. Okay, when you are optimize your structure, so it's a first step. So you are getting kind of, one second, I again show. No, this is not. Yes, these are okay. So in for the optimization, we will get kind of this much file. Okay, and in that file particular, there is a trajectory file, trj.xyz file. Okay, so in this xyz file, you have to just open over here, and one second. Yes, extension and animation. Okay, dynamic bond, click on the loop and just play. Now you can see that. Okay, how it's
oh,
optimized, we can easily see that. Okay, we can easily see that. So
okay,
it is a, I think it is a six step only. So it's sixth iteration. After six iteration, it's optimized. But in another structure, I think I will show you once different thing.
so this RG and all are sheet like, right, sir?
One second, one second. Let us see. Okay. So I don't know what is it, but let me show you. So this is a 46, huh? 46 step. Now look at it. Okay. So you can easily visualize this thing. Okay. So after
Okay, sir.
optimization, this just repel each other, not attraction. Okay. So this is a trajectory file. Yes.
Okay, sir.
Now what is your question? I don't get it.
So, sir, I understood, sir. With respect to atoms, we can visualize like this.
Yes.
But if it is sheet like or something, some other
No,
kind
you
of
you
structures.
can you can you can. This
Okay.
why I'm just showing the small atom or small molecules, because it's take a very much time. But it's time limiting kind of this thing. In workshop we cannot show, but you can do it for yourself. But again, I just one thing is remaining. Mm, So you can see that in basic in control, you just click over here, Rij cos x. Then your speed will be increase maybe 10 times. Okay.
Okay,
So
sir.
so you have to just use this Rij, because this is auxiliary basis set. Okay, so I don't know, it's internal mechanism why it's increasing speed and calculating energies in very much in minimum step. Okay, but you are using Rij cos x auxiliary basis set, and you can get your you can doing a faster way. Okay, but again, remember this thing, 100 atom is a maximum limit. Okay, you can do it, but if you have a workstation, okay, like a 48 code and all this. Okay, then you can do it. Okay, so for 256 ram and all this GB ram, then you can do it in your workstation, but in normal PC you cannot. Okay.
Okay, sir. Understood, sir. Thank you, sir.
Yes. So I think it's lunch time maybe.
So, sorry to interrupt you, sir. There will not be lunchtime. We will be continuing the valedictory function. Sorry to inform that one of our speaker, the third speaker, has met an accident today. So it is very unfortunate that he will not be available. So let us pray to God for his recovery of his health. So now we will be closing our program with the valedictory function. So I call upon Dr. Sanjay Kumar, the founder president, for remarks. Over to you, Sanjay Kumar, sir.
Yeah, thank you, Dr. Deepak. Yeah, good afternoon, one and all. Thank you so much for your active participation in this 2 days event. Am I audible, Dr. Deepak?
Yes, sir, audible.
Okay, thank you. And sorry for any kind of inconvenience during the event, like last session. So I hope you all learned a lot from this event, and I request from all to give sincere feedback and either any suggestions in the feedback form, which always give us to improve the shortcomings which you observe in any event or either talk or workshop or seminar, right? And I also request from all to join our association for doing some volunteer work for the nation. So kindly visit our site. Dr. Deepak, kindly share the link of our website in the chat box so they can join our community. So thank you once again. So please be with us for future collaborative work. Thank you once again.
Thank you, Sanjay sir, for your kind words. Today, we are very sorry that we are going to end the program here. So now let's call Mr. Kausal for the board of thanks.
Yes. So
Sorry to interrupt, sir, but if some of the participants want to say some feedback, we can give.
yeah, please.
Yes, you get sir, you can call the participants to give feedback on this platform.
Yeah. If anyone voluntary want first, then they can share. They can unmute and or they can raise hand. Then we can call them.
Today's sections are I am Swaminathan Pradhan. So today's section actually we are learn more actually, and sir also giving more knowledge. So today also we are satisfied with the today's section.
Okay, thank you, sir. Sir, we cannot see your name. It is just a number. So can you tell what's your name? 396717. We can see only.
Hello.
Yes, sir.
Am I audible?
Yes, sir.
I'm Manish Khare from Pune, and I just wish to say 3 points. Number one, thank you to AIP for organizing such a hands-on workshop on such a important and on such a topic which is, I think, without this we cannot think of any theoretical research or any condensed matter research in today's times. So, and the speakers which you have selected was so knowledgeable, and they were having such a command on their on the work which they have done, and on the use of this, that it's very it's very it's such an excellent and such a we may say that it had been more useful if you allow me to say 2 points, that what difficulties at my end I have faced I believe it has been with a pretty good number of participants. Number one, regarding the installation of the software, yesterday there was Arun Kumar sir sessions. He has given very good uh, say explanation about how to install, and you have emailed us the details about 2 days in advance. Still, um, because uh, some of us were very new to this and we were doing it for the first time. So at my end, I faced difficulty regarding Linux and Windows system like that. So to a certain extent, uh, I was able to follow up with what is being said and what is being done. At the same time, I was not 100% able. I was not able to follow up the 100%, but whatever 80 or 90% I have followed. Apart from that, the good explanation of the speakers gave me the confidence that the remaining 10-20% I can follow and do it on my own after the this workshop is over. So please forward us the recordings also, which will act as the basis for revising the concepts and all those things. And at the same time, the speakers were so open to the questions, and at the same time they were so so willing to help us also, because a person who knows good stuff does not always comes forward in such a and embrace the new learners. uh, it is not always the case is not always same, but here they were so ground to earth, and it was like we are talking to someone who is willing to help us. It was not like somebody is teaching us and we are learning something for the first time. So thank you so much to all the speakers and to the organizers as well. But please provide us with the uh, recordings, and regarding the assignment also, because I have to go through the recordings and then I have to work on the assignments. So the date which has been given for submitting the assignment, I think it has 14th. uh, if possible, please extend that date by at least 4 or 5 more days, because uh, uh, I would be doing it for the first time, so I have to learn and then do it. But yes, definitely we should be submitting our assignments. Thank you so much, and sorry for the long and detailed feedback. I'm so sorry for that, but thank you so much for this, and I'm looking forward to more such elaborate hands-on workshops, maybe 5 days or 6 days or 1 week, or maybe offline. That would also, the good thing about online is that anybody can attend it from anywhere. In offline, that limitation is there, but yes, the quality of learning experience of offline would be much better, I suppose. Thank you so much for giving me an opportunity to speak out what I wanted to. Thank you so much, sir.
Thank you, Mani sir. We have taken your words. So definitely we will extending our assignment duration for a few days. So thank you once again, sir. Is there anyone, any participant would like to share their experience?
Sir, myself,
Yeah,
Dr. Jitendra.
Yeah.
Sir, may I continue?
Yes,
Sir,
sir.
myself,
Yes, sir.
Dr.
You
Jitendra
can.
from a government college in UP, in Bundelkhand region. And it is a region, very backward region where my college is situated. And in government colleges, very limited facilities are available. So we are working with very limited facilities. During my research, I have done the coding using C++ and Python languages. So I have never used this kind of software. So it is very nice to learn. First time I am learning such kind of software, and I am very enthusiastic to continue with this kind of software to enhance my research. Thank you very much for the organizing committee. Thanks to AIP. And this session was also very interactive, sir. And I have a little request with organizers. Sir, I am unable to install the Linux operating system on my system, on my laptop. So kindly, if you give the choice for such participants which are not able to install the Linux operating system, some relaxation and assignment or some alternative to that, so we can also submit the properly the assignment. So thank you, sir.
Sir, thank you. We will definitely help you in installing the Linux for both the Windows, and it can be operated both Windows and the Linux definitely, and we will help you in the future. Thank you, sir. Yes, any
Okay, sir.
other participant that would like to share their experience?
Sir, I am Manjit. I have graduated from Amrita Vishwavidyalaya in MSc Physics in the year of 2022. So after that, I took a break from academics. I got a placement. So then I resigned from the job recently, and now I am trying to coming back to the research. So this was a great opportunity to boost again brush up my physics knowledge. Actually, I don't have any idea about DFT before the workshop. So the workshop has covered the theoretical aspect, and I got some idea about the hands-on. I'm so thankful to the organizers uh, and all the participants for nice interactions. Thank you.
Yeah, thank you, Manjit. We welcome you back, that you are coming back to the track in order to contribute something to the physics. Yes, any other participant would like to share
Thank you,
his
sir.
or her
Thank you, sir.
experience?
Yeah. Can I also say something? Uh, yeah. Good afternoon, everyone. I am Manish, and I am from Indore. And actually, I will be enrolling in my PhD course in this academic session. So it's kind of a very good learning curve for me to learn DFT, and also not just the like the theory, also but the practical aspect of it, because there are many YouTube videos and manuals tutorials everywhere, but the starting point was missing in all of these resources. But with the help of this workshop, now at least we all the I mean all the sessions were in such a simple manner that now we have a good starting point and base to work upon whatever research anybody is going to do. So thank you everyone, and thank you all the organizers.
Thank you. So I hope this might. Yeah, is anyone who wish to?
I will make some comments, because in this workshop I was worked as a I mean from AIP also, and from participant part also, because I also learned a lot of things. I wanted to do this because my MSc was from theoretical physics, and now I am doing PhD in material science. So what I thought is, in material science or in solid state physics, we synthesize a lot of materials and test them. So it will be always better to do it first theoretically, because we will not waste so much of material and chemicals. So some of you in this workshop also from material science background, so they will synthesis. Some of us are from theoretical also. So as a AIP member, I know that we all are helping each other, and we are a growing community. So we can help each other, theoretical as well as material science people. And one more thing, dual nature, I would like to say that Windows plus Linux. So many Windows laptops we can have, and we can dual boot that. So few softwares we can work in Windows and few in Linux. Or most of the time, I mean, my sir, who was also participant, he might have left just, Dr. Mansingh Takale. He was also suggested us in our MSc to learn Linux, because so much things are simpler, and most of the important thing is they are open source. So that's why we can use them with very ease. And so thank you so much. And I think I should hand over to Kaushal sir for vote of thanks. Thank you.
Yeah, thank you, Yogen. And
Yeah,
so
Kaushik,
I,
sir, sorry to
yes,
interrupt you.
sorry.
Yeah, if anyone is interested to give the feedbacks, kindly ask once again.
Sorry, I don't get it.
if anyone interested to give feedback, kindly
Yes.
ask once again.
Yes, please, please. Participants, please, if you give a feedback, so please feel free to say,
Yeah, all the
because
participants are requested to come forward to give feedback.
it
That
is a
will
motivation for us.
yeah. Okay, if there is no anyone, then you can proceed, sir.
Okay, thank you. So I'm very happy to announce that we will organize same workshop, but it is in molecular dynamics. Okay, MD. And again, we are not sure, but I think 3 to 4 software we will uh, uh, we will teach, or uh, we will organize this workshop. Okay, and using this 3 to 4 software for the molecular dynamics. Okay, it is also uh, important for the material science people. Okay, so this again, it is a very big challenge for us to organize this such a different background or different software for the DFT and even molecular dynamics. Okay, so thank you so much for the such a nice response. Okay, again, so first of all, I thank our patron in chief, Professor Rajeshwar Singh, to motivate us and organize such a nice workshop. First AIP hands-on. So this is our first AIP, first hands-on training on the DFT. Okay, so again, we thank to the our patron, Dr. Sanjay Kumar Singh. He is a founder president of the AIP. Again, our convener, Dr. Deepak. Thank you so much for the such a nice workshop. Our organizing secretaries, Dr. Ankit Kumar Mittal and Mr. Bia Jamir. Thank you so much for organizing kind of this such a nice workshop. Okay, and thank you so much once again all the participants. Okay, please interact with us and connect AIP and AIP member. And I think one thing is, I always uh, say that any workshop or any kind of symposium or a seminar or conference is just sharing your knowledge with each other and grow yourself. Okay, so again, this motivation for this workshop is same. Okay, we just mm, uh, doing research on this field. Okay, in material science, in whatever field, but we just uh, 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 collect, or you can say that collect information and sharing our knowledge. Okay, to each other and once again grow. Thank you so much. Yeah. Dr. Deepak.
Thank you, Kausal sir, for your word of thanks. So lastly, I would like to request all the participants to kindly visit our websites, and any participant who are interested in joining the AIP, we are most welcome. They are most welcome. And we also have, in the very near future, there will be a lecture given by the Nobel laureate also, which is going to be organized by our AIP and will be led by Dr. Captain Ritu Raj Singh. You can visit our website and you will see what we have done till then. And there are a lot of videos are also been uploaded. So please kindly visit to our website. And lastly, I request all the participants don't think it as a different from yours. Please think as your own family, and please kindly collaborate with one another in the research or in any field so that we can grow together, so that we can bring our country first and we can bring our country at the topmost in near future, maybe in 10 or 20 years, but after everyone will be coming to India for their job, for their research. Once again, I thank all the participants and the organizing committees who are involved in this event. So thank you all.
Dr. Deepak, kindly take a group photo.
Will it be possible? Yeah, please on all the cameras. So please give me for a minute. Please on all the cameras. Just give me a minute. Everyone, please on your cameras. Okay, thank you all.